welcome everyone to the machine learning discussion at the Royal Astronomy Society. I'm James, fourth year CDC student at UCL, and I'll be chairing the first session. So we really wanted today to be like a showcase of machine learning in the astronomy field. So we've lined up a huge number of talks, which means we need to be quite concise and quite structured with our organization. So speakers, these next few minutes are for you. So you're going to have 7 minutes to present, 3 minutes for Q&A. We'll hold up a sign when you have 2 minutes left of your presentation. Once the 2 minutes are done, the chair will stand, letting you know that you're now eating into your Q&A time. Okay? Once we hit the 10 minutes, regardless of where we are in the question, we are going to have to move on so that we have time for the next speaker. We want to be respectful to all of our speakers and make sure they have the necessary time to give the best talks possible. Are there any other notes that I'm forgetting? I don't think so. So with that, let's get straight in. Could I please invite our first speaker, Anne Kristen?
Okay. Hi, everyone. I'm Anne Miles from Royal Holloway, University of London, and I work in gravitational wave astronomy. So I will be talking a little bit about my machine learning application to this. So firstly, different types of gravitational wave signals. I'm going to focus only on the ones generated by compact binary mergers. Oh, sorry. So the ones by compact binary mergers. So either two black holes orbiting around each other and eventually merging, two neutron stars, one of each. Neutron stars are of particular interest to us because if we see them as gravitational waves, we can also, neutron stars can also be seen with the in the electromagnetic spectrum, right? So if we see them as gravitational waves and an EM, we get a multi-messenger event, which is super cool because we can learn lots about the physics of these objects. Okay, so when we detect these gravitational waves, we have got very noisy data. This is filtered data, it doesn't look this clean. And then we need to find, is there a signal or not? So we have got something called search pipelines. They're algorithms that do something called match filtering. So we have a waveform model from Einstein's equation, which we can match to what we think, so we can match what we think a signal should look like to what data looks like. And this is, when I talk about search pipelines, what we'll refer to, so these algorithms. They output things like false alarm rate, signal to noise ratio, but also template parameters, so like masses and spins of these objects that have merged. There are currently, it was in our gravitational wave collaboration, many different of these algorithms, so many different pipelines. So the question is then, if we have lots of different ones and they disagree, which one do we trust? And also, can we extract more information from the correlation between these different pipelines? And this is where the machine learning comes in. So lots of different pipelines, each gives us these parameters that I had on the slide previously, so like false alarm rate, masses, and so on. We can apply a machine learning classifier to combine them. But then there's a bit missing, the uncertainty. And this is the main focus of my talk. This is conformal prediction, which is a way to quantify this uncertainty on the classification. Because we don't just want to know signal or noise. We want to know it's a signal with this and this certainty, right? So let me go through what we've done. So we've got some data, these are the parameters I mentioned, and we've got mock data, so we know whether it's a signal or a noise, because they're simulations. We split it, we need training, testing, we also need calibration data, this is for the uncertainty. We train our classifier, measure the performance on test data, and then we quantify the uncertainty with conformal prediction on this calibration data. And don't worry, I will get to what conformal prediction is in a slide or two. But firstly, let's have a look at just the performance of the machine learning classifier. We have tried a variety of different ones. For example, XGBoost, a simple neural network, k-nearest neighbors, logistic regression. And we can see that all of them improve the ROC curve compared to the naive way of just taking the maximum false alarm rate, which is a simple way to combine all of these different pipelines. So if you're unfamiliar with the ROC curve, the higher to the top left corner, the better the score. So we can see that XGBoost does significantly better than the others here, which is great because we want our method to find more things. So what is conformal prediction? Usually when you have a machine learning classifier, for example, it could be any algorithm, you just get a prediction out. So in our case, a label. And conformal prediction gives you the uncertainty on this label. So here, very simple illustration. The first image, if I ask you what is it? It's a cat. We're all fairly certain it's a cat. Second image, what is it? Cat? Maybe the back leg looks like it could be a dog, right? And so we get two labels in our prediction set. The third image, really quite hard to tell what it is. So we've got three different labels that all could describe it. And this is how conformal prediction gives us an uncertainty, through these prediction sets. Now, of course, there's math behind it. So I'm not going to show all of the math, but the math promises us that the true label is guaranteed to be in this prediction set with a probability of 1 minus a chosen error rate. So if I choose an error rate of 0.1, I can say I'm 90% certain that that first image is a cat. And we can take this one step further and define the conditional confidence. So the conditional confidence on a particular label that we're interested in is the smallest error rate such that this label is included in the prediction set. And this is how we get our significance. Here we have a plot where we show the conditional confidence versus the max log alpha. We can see pretty good agreement. All of the purple ones are signals. Great, it seems to be working. Now let's look at some real data. So here we have the maximum P astro. It's the astrophysical probability of a signal being an event. Anything above 0.5 is defined as a signal. On the y-axis, we have the conditional confidence again. Again, everything above 0.5, we define as signal. You can see very broad agreement, right? Most stuff bottom left or top right, we agree either on signal or on noise. Bottom right, a few different things. Blue means only one pipeline founded. So if only one of all of our algorithms sees an event, we're less sure it's an event, right? So that makes sense. In the top right, we have three things. And one of them is a binary neutron star. Binary neutron stars we're very excited about. So far, we've only seen 2 of these events, so this would only be the third one. So if we could trust this up ranking, it would be a really cool thing, because third binary neutron star detected, super exciting. I should note that there's a caveat to this. We assume exchangeability for conformal prediction. So the calibration data, the testing data needs to be exchangeable, and since I said we train on mock data, test on real data, we cannot guarantee this exchangeable at the moment. So some further investigation is needed until we can see that this is actually proven results. And with that, I will wrap up. So I have introduced you to how to combine pipelines with machine learning and conformal prediction. We have shown that conformal prediction can increase the significance of events detected by multiple pipelines, and that it is possible to learn new things by combining the pipelines in this way. And I should also leave with a note that conformal prediction can be applied to any algorithm, so there are many other possible applications out there. Thank you.
Excellent. Any questions? So I have one. Would you mind describing, I guess, a little bit of your data pipeline going into your model? So you said you used XGBoost. What features are you actually putting into the model itself?
Yes. Sorry, but I must have been a bit far. So here we see the features. So this is our data. So the inverse false alarm rate is one of the features, and the signal-to-noise ratio, and then we have got all the template parameters. So this will be chirp mass, which is just a combination of the two masses we have. We've got spins and so on. So for each pipeline, we've got one of these. So we will have, if we have 4 different pipelines we combine, we'll have 4 different inverse false alarm rate features going into this.
Hi. Did you find the other 2 binary neutron stars using this method?
I believe they will be somewhere in the top right one. They're not all labeled, but I think they should be there because we would have pointed out if we downranked them. So.
Okay, well that's great for
We have not
people who
named
do
them all,
the optical follow-up.
Could you say a little bit more about the guarantee? You say that the label is guaranteed, which seems
Excellent. I have a backup slide on this. So this is the validity guarantee for conformal prediction. So if you walk through the math, which isn't on this slide, unfortunately, we get the guarantee that the true label is included with a probability of approximately 1 minus the error rate. This depends on how big the calibration set is. So if you have too little calibration data, this uncertainty will be quite wide. Yeah.
Okay, I'm just thinking if the real object has a completely different label which isn't in your set of.
That is not a possibility. You can only ever have one of the labels that we're training on.
Okay, in that case.
Yeah.
Any final questions? We've just had one off now.
Thank you. Thank you for your talk. It was really interesting. I had a question about if imagine your method was already calibrated. You got it from somewhere else.
Yeah.
Would that basically mean that your correction, or whatever you want to, like the calibration step would do nothing to that, and therefore you could use it as a way of validating the first method? Let's say it's a black box.
I'm not sure I fully understand.
If someone already gave you the outputs of this step, but didn't
Yeah.
tell you where they got it from, so the uncertainties with the predictions and so on, could you use your step to actually validate with the calibration data that they have indeed got the correct uncertainties and so on?
I suppose we could, yeah. I mean, there are very many different ways to quantify uncertainties. And if you have a non-machine learning algorithm, it is, of course, possible to get the uncertainties in a different way. But for the machine learning, it's really hard to get an uncertainty. So that is why we apply conformal prediction in particular. But yeah, I suppose you could compare and see whether or not they match.
Okay, thank you.
Thank you.
Thank you.
All right, yeah, hi, I'm Stephen, and I'm going to be presenting some work that I've been doing with these very nice people, including Sinan, who is there, and we'll be talking about something completely different after this. Yeah, so this is a model we've been building really to enable large-scale structure cosmology with photometric surveys. So these are surveys that map the matter distribution in the universe by observing the positions of galaxies and like their shapes or their clustering on the sky. And with photometric surveys, the challenge is you don't have such precise 3D information. You get good position on the sky, but you can't get the redshift so accurately. And so we've been kind of building a generative model for photometric galaxy surveys that hopes to address that in some ways. And so here's a quick sketch of just showing like what happens as you redshift a galaxy spectrum, and sort of when you're getting the photometry, you're just integrating it through these filters and just getting basically 6 numbers or so to summarize all the information that's available. So now I'll go through sort of in fairly general terms what I mean by a generative model, and then I'll add some more galaxy-flavored language to it, and then finally show you some results. So at the base of our generative model, we're going to have some intrinsic population distribution. So this is supposed to reflect the kind of true distribution of objects that's out there in the sample you're modeling. Then the actual sample you end up with is going to be some random draw from that, which will give you like a sample of intrinsic properties. And then there's going to be some sort of physical process that translates those properties into observable features, so like your galaxy photometry or spectra, for example. And then there's going to be things like observational noise and selection effects that actually take you to something that looks like real data. And the thing you really care about most of the time is the kind of intrinsic underlying population distribution that sort of is out there in the universe. And that's probably quite a difficult thing to represent. It may be a very high-dimensional distribution, weird shape, lots of correlation structure. So you can use something like a diffusion model to represent that, and that's basically a very flexible density estimator that kind of expresses your distribution as a sort of smooth deformation of something simpler, and then you learn the transform. And then in a sort of SBI type paradigm, you can constrain any moving parts in this whole chain by comparing the forward simulated model observations to your real data using some kind of distance metric or other measure of similarity. And then adding some more galaxy-coded language onto this. Our intrinsic properties are going to be physical parameters, things like the stellar masses, star formation rates, metallicities, etc. of the galaxies. The observable features are going to be model fluxes or SEDs, and then the mock observations are going to be like noised fluxes in our photometric passbands, which we're going to compare to a real photometric catalog. And to properly constrain something like this, you'll want to use maybe a really deep photometric data set to constrain the model, and then you can apply it to wide field surveys with less bands and less depth. And what's going to come next? Yeah, so once we've trained the model, we can do a bunch of different things with it. One of them is to sort of take off the parts of the model that related to our training data, and then add a new noise model, new selection model, and then make predictions for different surveys. So, for example, you could train on a very deep survey and then make predictions for a wide field survey. And then you can even go as far as, for example, applying a tomographic binning to your model galaxies and then inferring redshift distributions for a cosmological survey if you kind of go that route. Another thing you can do is take off kind of all of that stuff and then use that population distribution over intrinsic properties as a prior when doing inference for some particular galaxy you care about or some particular object you care about, by bringing in a new likelihood, some new photometry, and then doing a sort of more classical Bayesian inference type of thing. And then here is a cartoon showing showing all of that. Yeah, cool. In a more visual way. So at the base, we're going to have that population distribution over physical parameters. And for our particular case, we use stellar population synthesis as a parametric representation of galaxy SEDs. The SPS calculation, or an emulated version, which is faster and more GPU-friendly, gets you to noiseless magnitudes. Then some data model that learns how to apply realistic noise takes you to your noisy model fluxes. Then you apply selection based on whatever you have in the real survey. And then to optimize the model, you basically adjust all the moving parts until your model data, which is the kind of red cloud in this picture, matches the blue data as closely as possible based on something like, an optimal transport distance. And the idea is if you get a really good match in the kind of data space, then hopefully the kind of population distribution at the bottom should be representing the true population that's out there in the universe, which obviously we can't know directly. So some real results. We've trained this on Cosmos, which is a very deep field with 26-band photometry. It's really nice. 400,000 galaxies with a mid-infrared selection. We can use it to make population level predictions, as I said. So look at the redshift distribution in the field, slice up the population model to get the star forming main sequence. Also, work Sinan was doing looked at getting the cosmic star formation rate density and evolution of the quiescent fraction as a function of redshift and stellar mass. And then also, like I said, you can use it as a prior for SED fitting if you care about getting really precise redshifts for individual galaxies that are out there in the universe, like transient hosts or galaxies that are of particular interest to you. And Amit has been recently applying this kind of idea to kids as well, which is a wide field survey. So yeah, that's it. Yeah.
Questions? So I have one. You said that there's no way to directly look at that true underlying sort of population distribution. Are there other ways that you can probe to make sure that what's going on there makes sense, other than looking at the data at the end?
Yeah, it's a tricky one. You can, so some of the things we've done, you can obviously look at your, photometric predictions and see if those match with the real data. But then also you can look at potentially other probes, if there's different programs have, tried to estimate some of those properties, with spectroscopic indicators or stuff like that, then you can compare to the kinds of relationships they've seen in terms of their parameter inference, and sort of start to look at it in that way as well. And that's been a big part of what we've done, sort of comparing to different routes that people have taken to get at things like the star forming sequence and mass metallicity relation, all of that.
Yeah, I wondered how good your photometric redshift estimates are for upcoming surveys like Euclid, for cosmic shear in particular.
Yeah, so that's a good question. So I don't probably have a good plot for this here, but generally we've found that this is probably the closest thing I have to a plot. So this is showing galaxy level photometric redshifts, just posterior medians under our prior versus spectroscopic redshifts this is for cosmos galaxies. We've done this for kids as well now, and we've been also doing it. Madalena, who's there, and I didn't realize was going to be here, but she's there, has been doing this for LSST DP1 as well, and it's working pretty well. It tends to give more precise redshifts than, for example, a sort of broader prior over the SPS parameters would. We've compared a lot to Prospector in that context, which is a similar parameterization, but a less informative prior in some sense.
Thanks.
Time for one more.
Are there any interesting physical explanations for the extreme outliers in your plot there?
Yeah, that's a good question. Some of these are probably just things they're this kind of tail. It may be break confusion, where a Lyman break or a Balmer break has been misidentified kind of thing by the photometry, and there's certain limitations like that which will always come up. There's been a couple, I don't have the plot here, but there's been a couple where we looked at something where we disagreed strongly with the spexy, and it's pretty hard to tell what's going on there. It's possible there's some cases where there's been a line misidentification even, but obviously that doesn't explain everything here. But there's definitely been a few where we've looked at them and it's been the fit to the photometry has been so spot on. It's kind of hard to, you could definitely dig into individual cases and find some cool stuff, I think.
Well, thanks so much.
Thanks.
All right, perfect. Do I control the slides with this? Excellent. All right, hello everybody. Thank you very much for assigning me this talk. So as promised, I'll be talking about things that are relatively different. So this is work we've been doing for a while, actually, but together with Andreas Feist. But finally, we're gearing up towards getting this past the finish line at this point. And the idea is basically trying to map the morphological evolution from a population level perspective of galaxies using unsupervised machine learning techniques. So here's galaxies basically co-evolve. The galaxy properties and their morphologies have a co-evolution. Here's the classical picture, the star formation rate density from Pop Cosmos that's showing the evolution in the star formation rate density of the universe. So we see that it's basically almost an order of magnitude drop from redshift, say, 1.5 to redshift 0. And on the left, I have this figure from the Consolis review paper, which is showing galaxies that are disk-like galaxies, which are galaxies that, in the classical picture, they have spiral bars, they are more star-forming, and galaxies that are spheroid, which have sort of ceased forming their stars, and we can see that there's this increase in the spheroid galaxies that become to redshift 0, and a comparable decrease in the disk-like galaxies. What this model wants to do is to basically capture the entire morphological space, and that also includes things like mergers. So what we want the model to have is, if you have cutouts around galaxies, you would like to capture sort of the galaxies, the spirals, ellipsoids, whatever, the point sources, dwarf-like galaxies, but you also want to understand things to get things like mergers. And because mergers have a big impact on galaxy evolution, clearly, the hierarchical formation and growth of structure and everything, but ultimately, if you just look at a very simple figure like that, mergers have a big impact on the star formation rate of galaxies. So with the star forming sequence from this paper at redshift 1.5 or so, even there, mergers have the ability to push star formation rates at these really high levels that are sort of called starbursts. And locally, all the starbursts are mergers, so they trigger these really intense periods of star formation. But the way that mergers are identified, so traditionally we used a lot of these sort of non-parametric measures, estimates, sort of parameters measuring the morphology of galaxies. So here are 4 from, again, the Constellies Review paper for sort of a 1 to 3 merger simulated event. Here are sort of the usual suspects, concentration asymmetry, and Gini and M20, if you know the Jan Lotz papers. I'm not going to go into the details of them, but stage 4 is where it looks more like the merger picture, because galaxies sort of move around each other for a while before the actual coalescence happens. And at that level, sort of, for example, M20 has a peak, but ultimately you can see that these measures fluctuate quite a bit. And for example, things like Gini are sort of uninformative, even though Gini and M20, those two plotted together, is a way that people identify mergers quite frequently. So the approach that we have to this is we implement a variational autoencoder where we are not going to make these type of assumptions that are sometimes based on just visual cues, right? You expect a merger to have double nuclei, so things like M20 that is sensitive to that is a good metric to measure mergers. Sure, that obviously makes sense. But what we want is that we want the model to capture all those things itself, and we want the latent representation to be sensitive to all these type of cues, even if it's not visually immediately accessible to us, which most of the times it's actually going to be. So for this, we utilize this catalog by Kartal Tepe et al. It's HST candles, so it's part of the Cosmos observational field. And for those, that's sort of our testing and validation set. This is not a work on classification, but we're just going to use some physically meaningful classes to basically see what the model is doing is sort of sensible. And for those, we ended up choosing 3 different archetypes. There's sort of the point sources, maybe dwarf-like galaxies. There's undisturbed galaxies, which are not perturbed by any other nearby companion. And there are mergers and interactions. So it depends on what stage that you are. So moving on, here is sort of a cartoon that's representing the model. At the center, we have a CNN beta variational autoencoder. So for the convolutional neural network aficionados, it's a densely connected convolutional neural network. With the classical autoencoder strategy, what this thing is going to do is it's going to compress the input data into a latent representation that's much smaller dimensions than the actual input, and then it's going to try to faithfully reconstruct the input at the end. So what we are spending time on, even now currently, is tune some of the hyperparameters. What we use is a beta variational autoencoder. So by tuning the strength of the callback-Liebler divergence, you basically control the information bottleneck, and it's the trade-off between reconstruction quality and sort of the disentanglement of the important features in the latent space. But the paper that we are going to write basically is going to have a classification aspect to it, because then you can use the latent representation itself to actually make a classification to these archetypes that I talked about. So first, a visual validation of the VAE performance. There have been 2 epochs of this development, so this is the code that was still in TensorFlow. So here, the beta is adjusted so that we capture these high-frequency features as well. So now I've transformed everything into a PyTorch version. They are going to be published once the paper is out there. But ultimately, I'm quite happy with the reconstruction quality, which is really important. So here, beta is adjusted so that, it's maybe a little bit more diffuse in the noisy cases, but I'm still quite happy that it's capturing these, flux peaks. And like I said, there's still more tuning to be done. But ultimately, the point is that, for example, you can take a slice out of the latent representation, which is 8 dimensionals for us. In the 8 dimensions, I picked up 2 dimensions that were sort of informative in the morphology space that I like. And here, if you plot these visual classes from Kartal-Tepe et al., this is the type of thing you get, where the point sources, as expected, are really localized. And then you have an overlap between these undisturbed and merger types, which is also the type of things that you expect. But ultimately, you can see that the clouds are sort of distinct. And like I said, in the paper, we are probably going to provide this random forest classifier that is using the latent dimensions as the input parameters. And if you do that type of thing, on the left is the original figure, and on the right, here's what the model thinks is, mergers, undisturbed, again, only mapped into a 2-dimensional space. So it's a 2-dimensional slice out of an 8-dimensional space. But yeah, it is capturing these type of things that are distinct between these two sort of undisturbed and the merger type. And here, it's just an overall summary. The idea behind this work actually is to really dig in deep into this latent representation, look into what all the dimensions learn, to really disentangle, and to see if we can actually map a semantic morphological evolution on that space. And then the ultimate next step is to connect the work into with catalogs we can generate from PopCosmos to actually really see the causality, because there are still a lot of things we don't understand about. What happens first? Is it the changes in the physical properties, or is it the changes in the morphological features that happens first? So really dig into the causality there. And here's just a sum for people who might be interested in that, showing the distributions of these 3 in the latent representation. This is, of course, the 2-dimensional the 8-dimensional space just squished into 2 using the sum. But anyway, yeah, it's what I want to talk about today. So appreciate any questions and any chat about this. Thank you.
Hi, on the previous slide, why do you have that big clumping of point-like objects at the top of the plot?
So those are just how they are mapped onto the latent representation as the variational autoencoder is learning how to faithfully reconstruct the input data.
But why do they differ from the ones that are down in the rest of the distribution?
Just because they are very different morphologically relative to the rest, right? These are what our point sources look like, and then here's a galaxy that is very different. So they're mapped really far away in the latent, in those 2 dimensions, at least, in the latent representation.
Hi, I wondered if I could ask a question about the actual network that you use.
Sure.
Is that something you build yourself in TensorFlow, or is it off the shelf? And
It's something that I built myself.
okay, great.
So it has the traditional variational autoencoder approach, but for the convolutional blocks, I use the DenseNet, which is mapping what different blocks learn into each other as well. So the input isn't just what passes from the previous feed-forward layer. Every layer sees what all the other blocks before them ended up sort of extracting about the image as well. I ended up finding the best reconstruction quality with dense nets, for example, as opposed to res nets. But this is something that I built by hand, and I'll be publishing this once the paper is sort of out there.
Wait, can I also, was it a lot of trial and error? How did you kind of build those layers? How many layers did you have in the end? How did you go about optimizing the architecture?
Yeah, very good question. So the paper itself, of course, has some built in, so it has some prescription as to what they think are successful networks that were able to solve, like CFAR 10 or other ImageNet or other sort of computer vision problems. I started with something that I thought, because what I do with this work as well is that we try to replicate the Kartal-Tepe approach, where they made these 30 by 30 cutouts around the galaxies, and with only just a single band. That's where they were looking at to identify so for the proof of concept, that's exactly what I did, and 30 by 30 is about 900. So it's 31 by 31 or something, so about 900 pixels. So I thought which architecture might be the best to solve a 900-dimensional problem and bring it down to 8. So it was those type of things that, that led me to choose how many blocks I should be using for the dense net structure.
Great, thank you.
No problem.
Okay, thank you. We'll have our next speaker.
Right. Hello, I'm Jack. I'm in the final months of my PhD at the University of Sussex, and I'm going to be talking about how we can use dimensionality reduction, or DR, to help us compare galaxy formation models with observations. So I'll talk about why you might want to do this using direct observables and how DR is particularly useful in that case, and then what we can learn about the models in these lower dimensional representations. So this is kind of the landscape that we're looking at when it's comparing the physics of galaxy formation to our observations. So we have a simulation where we inform that with our understanding of the physics, and this gives us simulated galaxies described by their physical properties like stellar mass, metallicity, or star formation rate. Then from the observations, we have our observations from spectra or photometric fluxes, and then to get to the physical properties region to do comparisons, we have to apply this SED fitting stage. So we've already heard a little bit about this, but SED fitting is quite slow. So your most fashionable methods like bagpipes, it's going to take you about 100 seconds an object. And then if you really want to go to robust levels, that's going to be 30 minutes, hours, if not days. And then depending on what tool you use, when you actually get to that stage, the variation in your physical properties is actually quite big. So it's quite uncertain. So what we're looking at is what can we actually learn in the observable properties region. And to get here, we use SED modeling from the simulations, which is actually extremely fast. So with a modern tool like Synthesizer, every galaxy can be processed in less than 0.1 of a second at most. The problem we now have is that we have any number of filter fluxes or binned spectral or bin spectra that we want to analyze simultaneously. So in an ideal world, you would have your n-dimensional distribution binned, and then you can compare that between your observations and your simulations. But the problem is this is going to become very quickly sparsely sampled, so you can see the fraction of your robust bins. This is for 500,000 simulated galaxies, and when you get to 5 flux dimensions already, your statistics are destroyed, and your memory footprint is going right up, making them very difficult to handle. And then obviously all of this has the caveat as well that when you go beyond 3 dimensions, it's very hard to actually visualize and understand anything. But with DR, we can overcome this quite easily. So for those that don't know, DR, essentially, you have your n-dimensional distribution, and this code UMAP. It models that using a fuzzy topological structure, and then it searches for the lower dimensional embedding that best replicates that structure. So if you're like me and you know nothing about geometry, then you might think of a mammoth in 3 dimensions, and then once you apply UMAP, you get a squashed and slightly unhappy mammoth. The good thing about UMAP is that it preserves the nonlinear relationships between your input features. So this, so for example, PCA is completely linear. You'll lose information when you do your DR, but hopefully with UMAP we can preserve more of that information. There are other tools that do this as well, but they don't scale as well with dataset size and dimensionality, which is what we care about for large surveys. So for our sample, we're looking at the good south, and we have 8 JWST and 5 HST filters, so 13 filters. And then we're using all the publicly available simulated light planes that we can find, which is from 4 different models. We look at the flux and wavelength-dependent noise from the observations and apply this to our simulations quite simply. So we can apply consistent selection criteria to get 46,000 galaxies in total that are bright in F444W. Then we can apply UMAP. So we apply 500 runs of UMAP to account for its stochastic elements in searching for that lower dimensional embedding. And this takes us about 7 seconds per object of CPU time, so a lot faster than those SED fitting methods. We can then generate bin maps in this 2D space. So at the top here, I've got the density in each bin per square arc minute of observations. And you can see you get this horseshoe or slug shape. And then if we color this by the median magnitude in each band, this essentially traces the brightness of the objects, but the fact that this is a horseshoe and not a straight line tells us that we're preserving some additional information about the shape of the SED and not just the overall brightness. And then we can use a very simple metric to quantify the agreement between the observations and the simulations in this space. So one example is this bin-wise metric, which is the difference in density between the observations and the simulations, and divided by the uncertainty on that. But then we can also do, for example, the fraction of the different populations in each bin rather than the density. And then for each simulation, then you can produce a summary metric, which is the sum of this metric over the different bins. So we have one number that evaluates the agreement of the model and the observations using the number counts, your redshift distribution, and then the shape of all the SEDs as well. So what do we actually get when we do this? Oh no, my bracket's a lot bigger than it's meant to be. So we have these bin maps. So if it's blue, that means more observations in the bin. If it's red, then there's more simulations. And if I've put an outline around it with a specific color, it means it's only sources from that data set in the bin. So we can very quickly start differentiating between models. So Jaguar is performing the best, that's the lowest value of the metric, and then Sage is performing the worst. And you can see here that there's almost no blue in that Sage plot, which basically tells us that it's overestimating the number of galaxies. But the thing is that SCSAM and Sage actually use the same underlying dark matter model. So it's actually that the galaxies are brighter in Sage than they are in SCSAM, so they meet our selection criteria. So then I've redone this for SCSAM using a larger sample so I can bin at a higher resolution. And I'm now using the fraction rather than the density. So you can see that the SCSAM galaxies are occupying a completely different region of the parameter space. So to try and understand what's going on underneath, we can color again by medium properties. So we see that these galaxies they're young, they have very high specific star formation rates, and they're also accreting a lot onto their black hole. So we expect these to produce a lot of ionizing radiation, nebular emission lines. So the fact that these are in the wrong region of the parameter space implies there might be some issue with that aspect of the modeling. Then we can tune the hyperparameters to look at slightly different features. So now instead of using a Euclidean metric for the reduction, using cosine, and that essentially removes the normalization and just looks at the angle between the different input features. So we're looking at the shape of the SED now, and now I've normalized again by the fraction. So we're basically saying, do the simulations reproduce the observed distribution of SED shapes? And again, we still see that Jaguar performs the best, but now Sage is performing a little bit better, and it's Spritz that is the outlier. And you can see there are these very large regions of parameter space that Spritz can't reproduce. Then if we want to learn something else about the underlying physics, we can apply a degradation layer. So we can rerun UMAP emitting one filter in turn. And this is showing the relative scatter between the models. So if we emit F200W, there's more scatter, which implies that it's actually reasonably consistently modeled between the simulations. Then when we emit the longer wavelength filters, we get less scatter, implying that there's some variation in the modeling there. That's essentially everything. I'll just say this is not the ideal application. We're just using the kind of simulations and the data we have available. It's best for application to larger surveys and also to models where you're exploring parameter variations. You want to analyze those very quickly and consistently. Thanks.
Questions? So you said at the end that this is not your ideal sort of setting. Where would you like to take this work?
Yeah, so I think the ideal situation is where you have a model where you know very well the underlying physics and it's consistent, but then you're varying one or two astrophysical or cosmological parameters. Because then you can basically do this simulation-based parameter inference using this one metric that you get from each simulation. So it's very easy to differentiate between the models using that approach. And you can say, I have this one set of parameters that best replicates the observations that I have. So I think that's where it's really useful. And then also for these larger surveys, say, Euclid maybe doesn't have the filter coverage, but for larger surveys where you have a lot of filters, SED fitting is going to be too slow as we go to larger and larger surveys. And I think this will be a good alternative to that.
Thanks for the nice talk. Just to try to understand some of the terminology, you said it was mapping onto a fuzzy topological. What does the fuzzy mean?
This is the worst question you could have asked me.
I'm so sorry.
I've read the How UMAP Works section of the webpage many, many times, and unfortunately I just don't have the understanding of geometry to probably explain it to you correctly.
Okay, so we both need to go and do some learning about that.
But yeah, it's a lot of maths and geometry maths. Okay. But essentially, yeah, it models it. It makes a lot of assumptions and then models the n-dimensional structure in that way, and then it'll search for the lower dimensional structure that gives you the same structure. So you can quantify that structure using various metrics, and then you search for the lower dimensional one that matches those metrics the best, basically.
And is it some sense in that it's not a deterministic structure, but it could be, you know, is the fuzzy sort of trying to capture that it's sort of the shape of it as opposed to sort of the specific lines that you're drawing out?
Yeah, so the definition of structure in the n-dimensional space, it's not fixed, so it's actually a local structure, so each point has its own definition of structure, well, distance, I mean. So that varies, and then you have weights between each point in the space that determines whether the 2 points are connected in the structure. So, yeah, it gets quite complicated, which is why you can't actually really use distances between clumps in the lower dimensional space to tell you anything, or the size of clumps. It's more trends and general shapes.
Thank you.
Cool, thank you. Okay, so thankfully we are on time, which is great. So we're going to have a 15-20 minute break. The coffee room is just around the corner to the right. So we look forward to seeing you back at 1:45. Thank you.
Okay, hello. I'm Laura. I'm a postdoc at the Open University, but today I'm going to talk to you about work I did as part of my PhD at the University of Hull, which we used anomaly detection as an alternative method to identify cosmic chronometers. So cosmic chronometry is the estimation of cosmic age using astronomical objects. One method involves directly probing expansion or universal expansion. And this allows us to calculate the Hubble constant independently from cosmological assumptions associated with early universe measurements of the Hubble constant or late universe measurements that are associated with systematic uncertainties with the distance ladder, hopefully resolving the Hubble tension. So the basic idea is you take objects that formed at the same time and approximately the same redshift. After some time, thanks for laughing, we now observe those objects at different ages and different redshifts because of universal expansion. We can then calculate the Hubble parameter between any given two objects using the differential age-redshift relation with that difference in redshift and age between two objects. If we calculate the Hubble parameter for lots of different objects, we can then constrain the Hubble constant at redshift of 0. In practice, though, we use lots of cosmic chronometers that we then bin with these like orange and blue bins based off of redshift intervals, depending on the ages of the galaxies and their uncertainties. And then we calculate the Hubble parameter at an intermediate redshift between them. We can't just use any type of object, though. We have to use objects with a known evolution or cosmic chronometers, standard clocks. Typically, old objects work best, so old QSOs or old stars can be used, but we specifically want massive passively evolving elliptical galaxies. There's a lot of work that has already gone into these specific objects. They're characterized by a very rapid star formation right at the beginning of their lives, and then they have since evolved completely passively since then. This allows us to calculate their age very accurately. However, these objects are quite rare. We identify them with spectroscopy. We look for things like traces of star formation, recent or current, and essentially remove these from the sample. So there is the issue. These already quite rare objects are then made even rarer because we're then limited with how we're detecting them. So perfect example of machine learning. So we tried to train a machine learning algorithm based off of imaging alone rather than that spectroscopy. We then ran into the issue of, oh, well, spectroscopy hasn't actually given us that many cosmic chronometers. We ended up with 199 that had matching imaging in SDSS, unfortunately. So not a very large truth set. So perfect for anomaly detection. The idea was that we would train a machine learning algorithm or a model using the normal images, the normal galaxy images, so non-cosmic chronometers, and then treat the cosmic chronometers as anomalous data, feed that into the model, and then hopefully use some kind of loss as a flag. So we would expect higher loss because it's never seen these types of objects before. Yay. Our model is a convolutional autoencoder. Not typical architecture. We have quite a wide bottleneck and no flat or fully connected layers and no max pooling layers. We do this because we want the model to be really picky. We want it to be really good at recreating those non-cosmic chronometers and really bad at recreating the cosmic chronometers. When we use U-band imaging from SDSS, on the right we have examples of non-cosmic chronometers. They're much more elongated, they're much brighter against the background, whereas on the right-hand side we have our cosmic chronometers, which are much fainter and much more diffuse. In the R-band, it's much more obvious, but we don't use this for training. We then calculate the mean squared error. We found this works best between the input images of the autoencoder and the output images. And the idea was that we would just, the loss would be really, really high for the cosmic chronometers, and perfect, we just pick something and then done. Anything above a certain level would be a cosmic chronometer. In practice, this did not happen. We use a k-means classifier combined with U and GR colours. And this worked really well at separating the cosmic chronometers from the non-cosmic chronometers. The main thing was making sure that we didn't miss very many. And I'll skip this, but just take my word for it. UGGR and the MSC loss worked the best out of everything that we tried. It's very difficult classification, though. Like, our misclassified galaxies ended up looking very similar to the opposite of what they were. So our misclassified non-cosmic chronometers look very similar to our cosmic chronometers, and vice versa. Let's skip these bits to get to the good bit, the Hubble parameter. Big caveat, we only have 3 redshift bins, which is not enough to calculate this accurately. So we're just comparing the different subsamples. So our correct subsample is the 164 correctly classified cosmic chronometers. The missed subsample is those 164 plus 35 that were missed. They were misclassified as non-cosmic chronometers. And the false subsample is the misclassified non-cosmic chronometers, which results in the highest uncertainty. As you can see, we have a Hubble parameter value at 0.19 that could be -6. Very wrong. So that's good. That's sort of what we wanted. Finally, constraining the Hubble constant. Again, ideally, we would use more than 3 data points here. We're doing Monte Carlo sampling to try and fit these lines. The correct subsample has the lowest Hubble constant value, closer to early universe measurements, whereas the missed subsample has our highest Hubble constant value, which is much closer to late universe measurements, which I think is kind of cool. Lots of things to consider. Fixing those misclassifications is a big one, but also increasing our redshift range would help to increase the number of galaxies that we have in this portion, so we can have more redshift bins and hopefully calculate the Hubble constant more accurately. But in terms of a pipeline to identify cosmic chronometers to then flag for further spectroscopy to ensure that they are definitely cosmic chronometers, we think that it is quite successful, if I do say so myself. And hopefully in the future we'll use stuff like Euclid to increase that redshift range with the much wider area with vis imaging. Thank you.
Thanks for a very nice, well-motivated talk. When you're looking for anomalies, can I just check I understood right? Are you looking at the reconstruction error in the reconstructed image at the end? Did you also look for anomalies in the latent representation?
That's something I'd really like to look into. We didn't, but There is a lot of work, like we've already heard about, using that latent space as a classification. Hopefully when we have some more Euclid imaging, we're going to look into that.
Yeah, that'd be really good, because you often find different populations in that area. Great.
Exciting.
Thanks, which is really cool. I've never even heard of the field, so that's cool to hear about new things. So forgive my ignorance, but you mentioned, when you showed your CCs and non-CCs, you sort of mentioned in passing that in the R band, they were more clearly differentiable, but then you said you didn't train with that. That sounds like making your job harder when it doesn't, I don't know, so could you talk about that a bit more?
I'll get them up because they're gorgeous.
Thanks.
Yeah, so you would expect overall the losses to be lower. However, the big thing that we were very worried about was normal elliptical galaxies versus passively evolving massive elliptical galaxies. Very little difference. Okay. And the biggest difference we saw was in the U-band for imaging instead. But yeah, you would expect that R-band to be more important, but it wasn't for the elliptical galaxies.
Thank you.
Any other questions? We'll finish here. Thank you.
Thank you.
Hi everyone, so I'm Alicia, I'm a third-year PhD student at Oxford, and I'm going to be talking about how to use symbolic regression to build empirical dark matter profiles. So in the current picture of structural formation, galaxies form the center of this overdense extended halos of dark matter. And the main tool for studying the structure and the formation of these dark matter halos have been to use numerical simulations. They've shown that halos are roughly self-similar, and that their radial density profiles are well described by this NFW profile that is shown there, which has like this 1/r behavior in the inner part. However, there are a few problems with using profiles from simulation and then applying them to like real galaxies or clusters. For example, simulations depend on the dark matter model use or the implementation of baryonic physics, and these things are a bit uncertain. Actually, observations of dwarf galaxies and low surface brightness galaxies show that they seem to favor like a flatter inner core instead of the cuspy behavior predicted by NFW. So one might wonder, is there not a better data-driven systematic way of finding profiles directly from observations without choosing like a fixed functional form from simulations? And this is exactly what we're doing using this machine learning method called symbolic regression. So given a data set, symbolic regression tells you the best function to describe that data set. So unlike standard regression, where you fit the parameters of a chosen function, symbolic regression tries to uncover both the functional form and the parameters that best fit the data. This way, it can find analytic functions or empirical relations directly from data. Now, there are a bunch of symbolic regressions out there, but the one I'm using is called exhaustive symbolic regression, or ESR from now on. It was developed by my supervisors a few years ago. And in a few words, the way ESR works is like taking a set of operators, let's say like sum products variables, it combines these operators to produce functions. Now, once you have those functions, the real question is how do you choose the one that best fits your data? The simple answer would be to use a likelihood or a goodness of fit, choose the model that can best reproduce your data. However, this is prone to overfitting because more complex models are going to fit your data better, but are more difficult to then extrapolate to new data. So there has to be a trade-off between accuracy and simplicity. And in ESR, we do this using the minimum description length criteria, which is an information theory metric that ranks functions based on their description length, which is the expression that you see there, which has basically two parts. So the first part is just like the normal likelihood. The second part is the one that penalizes more complex functions, taking into account things like the number of operators, the number of free parameters, constants, and also the precision to which you have to specify your free parameters. So parameters that need to be more fine-tuned for the function to work, make the function less more complex or less simple. And so according to this metric, the best function is the one that has the slowest description length. Okay, so far I've described a method that you give some data and it tells you best function. To use this to build dark matter profiles, we need some data that can constrain the dark matter distribution. In this case, we're using weak lensing data. So as you probably know, weak lensing is the subtle distortion in the background galaxy shapes caused by the gravitational field of intervening mass. And because it's sensitive to all matter is a good way to trace the mass distribution of galaxy clusters. In particular, we're using data from the HSC survey, which has data from like around 150 galaxy clusters, and we convert the galaxy shapes to a measure of the excess surface density, which is the surface density at a projected radius r compared to the average surface density within that radius r. And you can see there an example of one of the clusters and what the data looks like. So putting all the physics together, what I'm doing is taking the functions from ESR to be our candidate dark matter profiles. These can be converted into a prediction of the surface density or the excess surface density that you can fit to the HSC clusters and rank using the minimum description length to find the profiles that can best describe the HSC clusters. Now, before I show you what the results look like, we wrote this paper first trying with mock data. So we generated some synthetic data using the NFW profile to closely resemble the HSC clusters in radial range and number of clusters. And then we model for every cluster the uncertainty as like a constant fractional uncertainty. And we wanted to try different noise levels to see how easy it was for ESR to recover the underlying NFW profile, which is what you're seeing in the plot there. So basically, for a very small fractional uncertainties, like 1%, 5%, ESR identifies NFW as the best model, so rank 1. However, as you go to higher errors, more like simpler functions can perform as well as NFW, so NFW is not the best model. However, the important thing from this plot is that even at very high fractional uncertainties, so like 80%, HSC is like around 60%, NFW is within the best top, like the top 10 models. So you should still be able to identify quite easily within your functions. So do we see this when we apply this to real data? Well, this is a ranking of the best functions found for the HSC clusters, and the thing that you can see there is that NFW is definitely not within the best 10 models. Neither are some of the other common use dark matter density profiles, and actually ESR identifies a lot of functions that outperform NFW. If you're wondering what these functions look like, there you have it. So this is for 2 different clusters, and plotting 4 models from the top from the table, and then you can see NFW as the purple line there, and 2 of the models are also written there, so they're easier to see. So 2 things you can see from here. The first one is that in the lower, in like the smaller scales, has like a shallower inner slope, and then it goes and that's like this peak. But the second thing actually is that, as you can see, all models give very different inner slopes, so it's not very well constrained by this data. This is because in weak lengthing, the errors are bigger in the inner regions than in the outer, so the likelihood is really driven by the outer points. But this is just a thing about symbolic regression, because it's given functions that really encode the information containing the data, and the data is just not very constraining in that part. So this is really telling us that the HSC clusters, when applied symbolic regression, they infer some profiles that are different from the standards models used without imposing a structure in regions where the data is weak. Now we're working on applying this method to data with like a better signal to noise, and also other probes that can better constrain the inner region, like galactic rotation curves. And if you're interested in learning more about this, or what I've just talked, or what other things you can do with these functions, actually the paper talking about this went on arXiv this morning, so you can find it there, or ask me any questions now. Thank you.
Did you investigate, say, bootstrapping some of the 150 out of your sample for training to have a look at whether or not these other profiles were being overfitted and to what level that was happening?
So, I mean, the metric already takes into account overfitting. So actually the thing is, like, most profiles are quite well, not quite simple, but in the sense that, for example, if you check that table, most profiles only have 2 parameters because the data is not constraining enough for functions to have more than those parameters. So I think that's like the metric is already accounting for overfitting. And the thing is, better data would probably allow for more parameters to be added to these equations, but this data is just not constraining enough.
Hey, thanks for your talk. It was really interesting. I had a question about when you say you're saying, for example, with HSC, NFW is not one of the best ones. But is it correct that you have some freedom when you're writing down your objective between the goodness of fit and the complexity and description length? You could say you want one of the terms to be more important than the other ones. So you have some freedom there about which thing you think is most important. So is it then fair to say one is better than the other in terms of the outputs?
I mean, you could change your metrics so that you have some freedom. So there's other things that you could do. I mean, here I'm using this. There are other things. You got terms as the CATS prior that takes into account how physical your equation is. You could put things like that. But we've tried changing a few of these things, and it doesn't seem to improve a lot because really the terms that are driving NFW to not be that good are the likelihood and this term with like the precision of the parameters. Sure. The rest of the terms, like the number of parameters and all the other complexity terms, don't really matter as much.
Well, just to clarify, can you not just multiply everything in part 2 with another number, and that would be a perfectly legitimate loss function?
Yeah.
Yeah.
That would be another metric. Yeah.
Right. Thank you. Is it really good?
Have time for a short question.
How do you constrain the things being Newtonian dynamics and not some alternative gravity?
We didn't. So when we were fitting equations here, we didn't put a lot of constraints into what equations could work or couldn't. I think we were just checking that equations had like positive density, like the equations were always positive.
So you may have evidence for Mond or something like that in your analysis?
Yeah.
Thank you. And thank you. I will move
Okay, thank you. My name is Andrew Green. I'm a part-time PhD student at the University of Hertfordshire, and I'm going to be talking today about field-level inference, field-level cosmological inference with generative diffusion models. So, why do we want to do this? Well, next-generation surveys, and indeed some of the older generation surveys, will allow you to get the full 3D matter distribution out of the results of the survey. And if we think about traditional approaches in cosmology, you typically calculate some summary statistics, like the power spectrum, etc., bispectrum, and then use that to infer cosmological parameters. Unfortunately, that loses information, so actually what we'd like to do is to infer the parameters or other cosmological information directly from the density field. In other words, and here's a picture of the cosmic web, so we'd like to take the information directly from that. So what are we doing with field-level inference? Well, really what we've got here, I think this is reasonably familiar to most people here, we've got an observed density field X observation, and what we really want to do is to calculate the posterior distribution of the parameters given that observation, and using Bayes-Pitt theorem, we end up with that middle relationship there. So it's related to the observation conditioned on the parameter, and in my case, we assume that the P theta, the prior, is uniform, and therefore we can, if we can get an implicit likelihood given parameters to generate an observation, then we can get what we need, the posterior. So how do we do that? Well, what we would like to do is to simulate density fields like that, and then come up with a method of obtaining the likelihood. Now, unfortunately, this is typically an n-body simulation, so that's quite slow, and it doesn't give you the likelihood directly. So how do we proceed? Well, fortunately, we can use generative AI and a diffusion model to give us both, and this is how we do that. So, what are diffusion models? Well, in my case, I'm using a denoising diffusion probabilistic model. It's based on the work of Ho et al. From 2020. And I'm training that using a data set generated by n-body simulations to generate these realistic 3D density fields conditioned on a set of cosmological parameters. Diffusion models come from the domain of image generation, so things like stable diffusion, which is a common image generator. You use models very similar to this, although not quite the same as this. The idea being that we have an image, or indeed in my case a density field, and then we can add noise to that until eventually what we end up with is a Gaussian random field, and then we train a deep neural network to a generative model to predict the noise in the image that we've added to the image. And then what we can do is then we start with the 3D Gaussian distribution in this space, and then progressively denoise it to generate a realistic density field, and one that's conditioned on a set of cosmological parameters. Now, what are the advantages of doing that? Well, diffusion models are relatively fast compared to, and certainly much faster than n-body simulations, and then you can actually go away and test it. Now, in this particular case, this is one of the prettier images, but actually you can go and test the normal summary statistics. You can test the power spectrum, bright spectrum, etc., etc. In my case, I've looked at the power spectra, I've looked at the density distribution, I've looked at a thing called the pixel peaks distribution, which is which measures information very similar to the bispectrum. But what this is doing is actually just showing that if you condition on the parameters, in this case sigma 8, you get you see a difference in the clustering. So what do we actually need to do, though, is we need to get that likelihood, and in fact we actually can do that with an implicit likelihood, and then if we get the likelihood, then we can actually plug it into more standard MCMC techniques. Diffusion models do provide this computable thing called the variational lower bound, and for a conditional diffusion we know that this is true. We can get a formula for that, which is based on the steps of the diffusion model. It's in the slide deck a little later on. And you can use that to generate a surrogate likelihood given an input density. So, and then that allows you to plug that into your standard MCMC samplers. Now, what are the challenges of doing that, and where I am in my work? It's still the case that variational lower bound is computationally expensive to do, because basically to do it properly, you need to go through all of the steps of the diffusion model. And for a standard density field that I'm working at 128 cubed, that it still takes about 4 minutes. That's still rather slow. And even generating those samples, it is quite slow. So how do we do that? How can we improve on that? Well, actually, it turns out that actually you don't need all of the terms in there, and you can get away with a relatively quick approximation of the first 15 terms, and then a very fast quadrature to get a good approximation for the VLB down to about 1% error. And once you've done that, then you can plug it into these samplers, and that's where I am at the moment, which is to plug that into standard samplers and then generate the posterior. So just to conclude, diffusion models do fortunately allow you to provide an emulator that you can test independently of the Bayesian framework, and it provides a way to obtain the VLB, gives you the likelihood, and you can get a very efficient approximation for that, which takes roughly 4 seconds per sample. And then the next step is to then go and look at using that to generate the posteriors, and I'm also going to be looking at some alternative generative models that also produce convenient ways of obtaining that likelihood. And I'll leave you with some pictures of density fields which have been generated by the model. These are four density fields with 4 different cosmologies, and I'll pause there for questions.
You said that the VLB approximation was very good. Is there like any region of the parameter space where it's not as good, or is it like?
Sorry,
And you said the approximation of the VLB is really good. Is there a region in the parameter space where it doesn't perform as well?
It's generally quite good. I mean, you can sample, and I've done quite a lot of sampling and looking at it empirically. And what you end up is that I don't have a picture of it, but let me find the calculation. The calculation is, let me see if I can find the calculation. The VLB is here. So that's the expression for the VLB. And broadly speaking, there's an end term, and then it's a sum over the Kullback-Leibler divergence. And it turns out that actually in all cases this is very strongly exponential form for this function. And then you just need the first small number of terms. And I mean, it's an empirical, you have to do it empirically. There's no proof that that is the case, but empirically it's definitely true that that's all the samples I've looked at do generate that exponential form.
Thanks for the interesting talk. I was going to ask, do you have any intuition for why a diffusion model-based approach to modeling the likelihood might do better than sort of traditional neural density estimators, for instance, where you do field level inference and you just train a much lower dimensional neural density estimator?
I think so. One of the advantages is it's kind of a byproduct. It kind of comes out of the box of the model itself, and so I think that's one of the advantages. And you're not imposing a form on the distribution. So those are perhaps the advantages over other techniques. This particular model, the DDPM model, does generate it in this form. Other models, like score-based models, also generate similar types of approximation. But that's really it. It's just it comes out naturally from the emulator model. Okay, thank you.
Right. So, hello everyone. My name is Austin. I'm a final year PhD at Southampton, and I'm going to be speaking about Speculate, which is our brand new emulator-based inference framework for accretion outflow systems. Let's start basically, why do we need this tool? Well, a lot of times in astronomy, we're now gathering record amount of observational data. We've got loads of different spectra being produced from accreting systems. And you come out and you might see something that looks like the spectrum on the right, where you've got a lovely P Cygni profile on the carbon-4 line. Now that's a telltale sign, you've got an outflow, but you're not necessarily sure what parameterization of your system will lead to that outflow. In essence, working out if there's any new fun physics associated with that particular system. So, how do we end up working out what that is? Well, a lot of the time we always have to compare to various models. And then we compare model with observation. If they match up, you can probably be safe to say it's along those lines in its parameterization. So what do we do to model? We use a program called Sirocco. It is a ionization and radiative transfer code for these accretion disk winds. You could sort of see there's an MHD simulation on the left, what one of these winds particularly would look like. And what you would do is observe along one direction of that wind, and you'll generate your spectrum, and then you can use that to necessarily compare. However, there is one main problem with this, is the fact that this is quite an expensive code. There is upwards of 30 plus input parameters we got. Let's say we take a really coarse sample of 3 values each. In terms of computational time this will take us, that's about 11 billion years. So, problem. How do we solve that? Well, this is when we turn to emulation instead. Now, quick definition of the emulation is basically it's a machine learning method that approximates the behavior of a more complex system, in our case here, Sirocco. And the whole point is you basically take your input parameters, pass it through your emulator, and you get your spectral output. And the whole idea is this is much, much faster to do and sample from than your simulation. Given it's a machine learning technique, it naturally needs data, and even though it is computationally expensive, we've basically had to create one of the largest synthetic libraries of accretion disk wind spectra in astronomy so far. Currently, we've got one system out there for categorized variables. We've got a data set there that's released on Hugging Face. We're currently running doing the computation for one with AGN. And essentially what this is 9 varying parameters, which are the most important ones we associate with our model, coarsely spaced, so 3 parameters each. We do as wide a range as we possibly can, because naturally emulators, they're basically fancy interpolators, and interpolation is a lot easier than extrapolation. We take that data and we feed it through our architecture, and we are running a principal component analysis Gaussian process emulator, which is a little bit different to sort of the neural network approach for interpolation, which a lot of people have been sort of doing. The main reason for doing this is actually the Gaussian process gives us an uncertainty quantification associated with the emulator itself, which neural networks doesn't necessarily do. Does mean there is a bit of computational cost associated with that, but we can do some optimizations around that. Primarily with, for example, PCA, it reduces that dimensionality down, so we've got a more workable matrix. Because I think, particularly at one point without these optimizations, I think one matrix to convert was several petabytes, which isn't necessarily a great thing to do. There was one other cool thing we added as a tweak is we modified a likelihood function essentially. And this is basically adding a different kernel with the Gaussian process kernel. And the whole idea is it addresses the fact of mismatches between your model and your observation in terms of line strengths. Because one of the hardest things that we end up having to do is actually, for modeling the particular line strengths, it's just difficult. There's no other way to say it. It's just a hard approximation. So we don't want that to dominate when we're evaluating against our observation. Finally, you've got a working emulator. This is basically sort of a prototype early on we had. We've got the green line being the emulator, blue line being the existing data frame, i.e. we want them to match up pretty well. They do that fairly decently. That basically means we've now got our emulator, we've got our observation, you can plug it into your favorite MCMC system, and you can start sampling the parameter space associated with that. Now, that's really cool. However, there is one last problem left, is we're trying to advertise this as much as we can to observational astronomers for them to use. As a result, there's a lot of complexity numerically, machine learning, and we kind of want to make it easy for them. So, this is where I want to show off essentially our little interface, and I'm partly doing it because it's cool and fancy and it's really easy to use the program as a result of it. But also, I want to advertise a thing called a Marimo notebook. It's on the top right. And it's really cool, and everyone should be using it as best they can. Essentially, it is a Jupyter notebook, but better, right? It runs entirely off .py. You can build app interfaces by clicking and dragging cells to different parts. So you can build these really easy interfaces for it. It is reactive, so you can run cells in any order, and you can only define a variable once, which is naturally good Python practice. But it means you can set options and settings and get your code to iteratively change without actually having to run different parts. So you can really guide the user to making it work as easy as you can. And it's got really cool things. It's got sliders, drop downs. You can drag your observational spectra, so it's really easy. They just click run, and then it gives them their outputs. So with that said, this is going to be a test. It technically runs on mobile. Because it's on a Hugging Face space, it is designed for a computer, so an iPad's probably better, but it can run. So if you can have a play, have a look, have a follow of what we're doing. We're just finalizing the inference part and getting it to the user interface, and then it should be coming out very, very soon. Cool. Questions?
Any questions? For the online version, like, can people also create their simulate their own data and use it?
Yeah. So well, to actually get the Sirocco data behind it, you'd have to go into that program. The whole point is we hopefully give a comprehensive enough grid that they don't have to, but then they can train their own emulators for their specific things. So if there is a particular wavelength region they want to target that's not existing, they can make it very easily. It runs fairly quickly at this point, and then they can do what they want with their spectrum depending on their needs.
Can you be specific about two parts? What computational resources are required for your Marimo environment for it to actually work speedily, etc., because I presume you're using the default Hugging space. And then how much computational resources are you saving using your emulator? Have you had a look at what your reduction is?
So yeah, there's when we sample with our emulator, at a minimum time for a Sirocco simulator, it's going to be about 30 minutes to an hour. When you do it sampling through the emulator, you're on the order of seconds. Now, we are providing different styles of, well, different sizes of models, basically, so it can tailor for the computational resource that you have. So you can run it on laptop for smaller grids, and it runs all the way up to sort of H100 standards. And we're actually going to basically make a little neural one as well. So if you really just want to demo it, and it's basically instant as a flash in that sort of sense. But yeah, that's the sort of level of speed up.
Not specifically time, but things like VRAM threads, because time is depending on how much you throw at it, because I could give you 100 cores.
So again, it's basically there is a bottleneck with the Gaussian process on the matrix size, which is directly related to basically how much memory. We do some optimization in terms of sparsity of the matrix to try and reduce that load, but we are talking on the orders of gigabytes of VRAM for our better models. And that's sort of why we've also limited ourselves to the 8 and 9 parameters, because at that point, each time we take a step in parameter, we're scaling by an order of magnitude. So we'll be hitting hundreds of gigabytes in terms of VRAM usage, that sort of thing.
Any other questions? Then let's thank Austin again. We will now have the lunch break. It's 1 hour, so we'll see you back here at 1:35. Thank you.
Welcome back to the afternoon session. I'm Rosie, I'm going to chair this one, and I'm going to throw you straight over to our first speaker, Andy Wilson.
Thank you. I'm a postdoc at the University of Exeter, where I'm conducting research into young stars and star formation. Today I'm going to be talking about a machine learning classifier we've built for finding candidate young stars. I'm going to start off with a brief introduction to naive Bayes, which is the kind of classifier we're using, then our particular young stellar object classifier, and just finish up with a few of our results. So naive Bayes is frequently overlooked in favour of more sophisticated forms of machine learning, yet when it's well constructed, it can actually perform remarkably well, and it's especially good at the rank ordering of sources in classification problems. It also has the advantage that a simple algorithm means that you can trace the posterior probabilities, which it outputs, back through the calculations into the input features, meaning that it's an explainable form of machine learning. And that allows you to sort of easily, when you get unusual or unexpected results, you can trace them back and understand reasons and sort of troubleshoot any problems, as well as it helps for tuning the classifier to get better results. Now, the Bayes is based on the inequality that the posterior probability is proportional to the likelihood multiplied by our prior knowledge. We've built a binary classifier which selects between the classes of whether it's a young star, a class 2 young star object in our case, or something else, which is the term other. And the standard form of the naive Bayes is the middle equation. However, we reorganise this as in the bottom, and then look to the final term in the bottom left. What this does, this illustrates how it is that naive Bayes makes its classifications. And what it is, it's the ratio of the likelihoods. The likelihoods are probability distributions of the classes by the features. And I'll come on to that in a little more detail in a couple of slides. For our young stellar object classifier, rather than just throwing lots of data into the classifier and letting it work out what's good for identifying young stars, we decided to use our astrophysical knowledge to then select and create 5 features which we expect to be good at identifying young stars. We have a mid-infrared and a near-infrared excess feature, which are good for identifying the disks around young stars. We have an H-alpha excess feature, which detects the accretion. Young stars lie above the main sequence on colour magnitude diagrams. So we've got another feature which is based on colour magnitude diagrams. And finally, young stars are highly variable. So we have a feature that's based on the Gaia G-band photometric statistics. Now, back to the likelihoods. For our training data, we have a set of known class 2 YSOs and a set of sources which return other sources which are not YSOs, and we expect to have very few or no YSOs in that data. Now, the likelihoods can, in a simple form, just be the probability distribution of the training data. So here we have our mid-infrared feature, which is Y is W1 minus W2, and the top is just simply the probability distribution, the histogram of that training data. So you can have the others in blue and the YSOs in red. Now, some simple implementations of naive Bayes just use Gaussians to represent the training data. We don't believe that does a very good job at building a sort of good quality classifier. So instead what we do is we use kernel density estimation, as this follows the training data more closely. However, once you get to the wings, with the small amount of sources and the low numbers and the small number statistics, we find it's difficult to get good results there. So instead what we do is we take just a very simple approach. We take the proportion of the training data in the wings just to define a simple pure probability. And you can see the results of this in the bottom plot on the right, where we have the ratio of the likelihoods, whether it's a C2, which is, in a sense, whether it's a young star, divided by the likelihood of whether it's other. And this starts for low values of the feature, weakly favouring a classification of other, through a transition region, until it very strongly favours a classification of a young star. We have a published version of our classifier in monthly notices, Wilson et al. 2023. For this, we ran the classifier on a region of the northern galactic plane. And what you can see here is a set of high-confidence YSOs from that data set. And these are displayed in galactic coordinates. The middle plot is exactly the same, other than we pointed out known young clusters and star-forming regions. And what's encouraging is that many of the groupings of stars which we see are lining up already with where we know or expect there to be young stars. Then the bottom plot, all we've simply done is replace the galactic latitude with distance by inversion of the Gaia parallaxes. And what's also encouraging here is they're concentrating in distance space as well. We're working on a new version of our classifier, which we hope to publish in due course, where we've improved each of the features, but we've also gone from a region of the northern galactic plane to the whole sky. So our new data set is based on 127 million sources. And what you have here is this is just the average looking at all sky. We only go out to 2 kiloparsecs because we want to restrict it to regions where we have the distances are well constrained by the Gaia parallaxes and uncertainties. And what we have here is yellow and red is where the average of the sources in that pixel are more likely to be a young star. The likelihood ratio is favouring that there are more young stars there. And you probably start to see some sort of features in there. And although this is, in a way, indicating where there may be young stars, at this stage with just one feature, it's really sort of a map of variability in the nearby Milky Way. But it also illustrates the way that naive Bayes works, because you can kind of dismantle the different bits to kind of look at how each of the features works and influences. And you can actually see down in the lower right, that's the Orion star-forming region. Finally, one thing which we're doing, which we think should be quite novel, is our team is a member of the WEAVE stellar, circumstellar and interstellar physics team. WEAVE is a new multi-object spectrograph being commissioned on the William Herschel telescope. And over the next few years, WEAVE's going to obtain spectra for several tens of thousands of our targets in our classifier catalogue. What this allows us to do is, from those spectra, we're able to analyse them to work out which of those stars really are young stars and which of them aren't young stars. And that allows us to recalculate our confusion matrices, but also it will allow us to recalibrate the posterior probabilities into genuine probabilities. One thing with naive Bayes, and I think some other forms of machine learning, is you'll get a posterior or probability out of it, but a 50% or an 80% posterior doesn't mean a 50 or 80% probability. From this data, we should be able to then recalibrate those to be actual genuine probabilities. And here, just to summarise, thank you for listening.
Fabulous. Thank you very much. I'd like to open us up to questions in the room or online.
I just had a question about the naive Bayes classifier. So I think naive Bayes has some strong assumptions that makes it tractable. Does that affect your results?
Yes, I mean, the key sort of thing with naive Bayes is it kind of assumes there isn't correlation between the features. So if you do the full Bayes, then you'd sort of have all those correlation terms. But what those correlation terms tend to do is sort of tweak the posteriors rather than entirely changing the sort of posterior probabilities. So you'll tend to get, so it won't be quite as good as going full Bayes, but realistically, it shouldn't make a dramatic difference, but has the advantage of computing speed and the amount of effort involved in creating it.
Thanks.
Lovely. Has anyone else got any questions?
Sorry, if I could just ask one. So if you could go back to your plot where you showed where the location of young stars are. Yes, this one. This might be a naive question, if you pardon the pun, but how much of this could just be a function of the population of overall stars rather than just young stars?
So what I haven't shown or had time to show is kind of all the other plots, but the distribution here isn't really related to the source density, which we see if we just populate that. What we do have, though, is artifacts from the Gaia scanning law, because this is based on Gaia, and there's some parts of the sky which Gaia has visited many more times than others. So you can see some of these curves and arcs here. Those aren't actual kind of real features of the galaxy. Those are features where actually there's been more visits by Gaia, so actually there's better quality data there than some of the other regions.
Lovely. I think we have time for one more if anyone's waiting for one, or if you've got any online.
Or if not, I'll point out one interesting feature on here, which you might notice around minus 30 degrees. That's the Large Magnetic Cloud. Now, this is only supposed to be out to 2 kiloparsecs, but what happens is, because there's a great many sources there, even though we restrict it to good quality parallaxes, a few sources sneak through in the background from the magnetic cloud, so even though it's much further away. So it's just one thing to sort of be aware of when sort of working with Gaia. We have another version of the data set where we do an even stricter cut on parallaxes, and then that disappears.
Okay, amazing, very interesting. Thank you
Thank
very
you.
much, Andy. And could I invite our next speaker, Tara Tassin, to come up and
Hi everyone, I'm Tara. I'm in the exoplanets group at UCL, and today I'm going to be talking about my work trying to speed up atmospheric simulations. Okay, so first of all, how do we model atmospheres? Well, when we're considering atmospheres, there's various physical processes that we would like to model. So, for example, the chemistry in the atmosphere. We want to model cloud formation, radiative transfer. So that's how radiation from the star or from the ground interacts with the various molecules in the atmosphere. And for each of these processes, we describe these by using time-dependent differential equations, and we solve these equations across a grid representation of the atmosphere. So what we have is we initialize the state of our atmosphere, and we iteratively run this numerical solver. This will tell us the updates across time to our atmospheric state. And then once some sort of stopping criteria is achieved, we can output our final simulated atmospheric state. So there is a problem with this, though, and that's that these models are highly computationally expensive. So we usually solve these integrations using some sort of numerical solver. But when doing this, modeling one atmosphere can take of the order of weeks or even months to output a simulation. So this vastly limits the utility of these models. There has been a lot of work trying to use machine learning to mitigate against this. So this would be using an emulator to replace the calculation of such an integral. So these emulators are often trained offline, so you need to generate large training data sets to do this. And common models that you use are typically neural networks or recurrent neural networks or some sort of deep learning model. But yeah, so problems are training data costs, and also the generalizability across parameter space. So when you're training an offline model, the flexibility of the model across input parameters is highly dependent on your data set that you're using. And this is a problem in exoplanets where we have a vast array of atmospheres under different kind of temperature, pressure conditions, and we would like the emulators to be able to handle all of this, but that's quite tricky. So my work has been trying to mitigate against these two problems with commonly used emulators, and so the work's called adaptive online emulation. So I'll just give you a very brief overview of what that's trying to do. Okay, so consider we have a simulation that we're running, and you're starting at time step equals 0. We can run n time steps using our traditional numerical solver, so no machine learning at all here. And we can collect the data from all of these time steps. We can then use this to train an emulator within the simulation, and then deploy this on the fly. So doing this, you are using a very kind of narrow data set corresponding to what you've seen so far in the simulation. So your emulator will eventually incur drift. So what we do in this framework is to switch back from the emulator to the numerical solver, collect some more samples, and then update our emulator. We then continue in this sort of kind of repeated process of deploying the emulator, collecting more samples, and then updating it again until our simulation is complete. So under this framework, we don't use the emulator for all of the time steps like you would with an offline emulator, but you do use it for a large proportion. So this should be able to incur speed up, and that's provided you have a machine learning model which is data efficient. So that means it only needs a small number of samples to train to good performance, and which is fast to train as well. So to do this, we use extreme learning machines. So if anyone hasn't come across extreme learning machines, just think of a simple feed-forward neural network. So the weights mapping from the inputs to the hidden layer are randomly initialized and fixed, so we don't optimize these at all. The only weights which are optimized are the ones which I've labeled beta here in red, so that's mapping from the hidden layer to the output layer. So doing this, this means that you don't need to backpropagate any weights. You can find a closed form solution for beta, and this means that it's really fast to fit these models, and you can find the global minimum solution. This also gives us a nice kind of way to get a very fast update formula for these models as well. Thanks. Okay, so using this adaptive online emulation with the extreme learning machines, I've done a proof of concept on an exoplanet GJ1214b. So I've run a simple simulation of the temperature profile for this planet. I've done it in one dimension just to make it, it's just a proof of concept. And to model the temperature profile, you need to be solving the radiative transfer equations. So these are quite computationally heavy because you're modeling the movement of radiation, absorption, emission, scattering by various molecules. So it is a good target for us to emulate, to speed up. Okay, so this is a kind of schematic of my simulation. We have a spin up at the beginning to get to roughly the area of parameter space of interest, and then we have a data collection phase. So that's all using the numerical solver. We then train the extreme learning machine, which takes approximately 3 seconds, and then we deploy this and do our adaptive emulation until the end of the simulation. Okay, so I'll show the results. So what you're looking at here is the y-axis is altitude, the x-axis is temperature. The blue line is the initial temperature profile of the simulation, so that's t equals 0, what do we start off the simulation with? So the black line is from a completely numerical simulation, so that's no machine learning at all. And the red dashed line is the temperature profile coming from our AOE simulation. So by eye, we can see that they are overlapping, they're quite close. Looking at the residuals, we achieve up to 0.01 mean absolute percentage error between the temperature profile of our simulation using machine learning compared to the reference simulation. So that is by far good enough for our scientific purposes. And what is the speed up? Because that is the point of the whole exercise. So for this simulation of 200,000 time steps, we got over 11 times speed up. So that's a 91% reduction in the time for the simulation. That's no offline training costs, no offline data generation costs. All the training's done completely in the simulation. And bigger speed up is possible for longer simulations because the initial training cost is amortized over the length of the simulation. That's what I'm showing in that graph there. Okay, so that was a very brief overview into that work. So if you are interested in the details, then do scan the QR code or drop me an email. My email address is there. Thank you.
Fabulous. Thank you so much. Have we got any questions for Tara?
Thank you very much for that. I was wondering, during the emulation phase, how are you handling any sort of instabilities or dissipative natures which sometimes occur in numerical models? How are they handled?
During the emulation phase?
Yeah.
So this work is it's at the beginning stages. There's a lot of other plans I have for it. So within the framework, I would like to put some sort of safety monitoring to see if the emulator is not performing well enough, then we can switch back to the numerical solver. And some ways in which I was thinking about doing that are we could have a simultaneous sort of anomaly detection model going on at the same time, kind of looking at the inputs to our emulator and seeing, okay, did they diverge too far from what it's seen during the training set? If they do, go back to the numerical solver. Because at the end of the day, this surrogate model is just an interpolator, as was said in one of the talks before. But yes, I'm thinking about how to do that so the emulator is used in a reliable way.
Lovely, thank you. And one more question, gentleman in the middle.
Thanks, Tara. You showed an impressive result for the error bar, the deviation.
Thank you.
It's a generic question I have about emulators. When to stop? When do you decide it's good enough? And I guess the answer is, the generic answer is, depends on the application. So I wonder, with 0.01%, that's it?
Yeah.
Or do you want?
No, you're right. It definitely depends on the application. So for this is a radiative transfer emulator. And it's trained on a model which is a two-stream model of radiative transfer. So that's to say that the model it's learning from already has a lot of assumptions and approximations in, and so isn't a perfect model for radiative transfer. And so you can consider like the margin that is good enough as being like the margin of error that your models that you're already using are incurring, I suppose, and that's application dependent.
Thank you.
Fabulous, and thank you so much, Tara, again.
Thank you.
Fabulous, and our next speaker is Simon Joyce.
Hi everyone. I'd like to just present some work I've been doing on Mars, looking at Mars and using AI to help us to analyse the data that we're getting. So this is using data from Mars Express, which is an orbiter, and it's been orbiting Mars for about 22 years now, so it's very successful. And one of the instruments on board the spacecraft is the ionospheric sounding radar. So this is just a schematic to show what that does. It sends out a radio pulse from the spacecraft which reflects off the ionosphere, and we get this is the data that we get from it. So it's basically a map of where the reflections occur as the radar pulse is passing through the atmosphere, and you can see the green kind of horizontal line, that's the reflection off the ionosphere, that's the signature that we're looking for. One of the great things about Mars Express is that because it's been running for so long, it's built up a huge database, and we now have about 2.3 million ionograms, which is a huge amount of data. The problem with that is that no one has time to look at them all, and ionograms are typically something that you have to interpret manually. The normal way of analysing them would be to look at it and to click on the pixels where the ionospheric trace is in the image. and then use that to extract the measurements of the altitude and the frequency where the ionosphere occurs. So we wanted to try and automate that because there's a huge amount of data which is not currently being used or analysed. And the first step we wanted to do was just to classify the ionograms as to whether the ionosphere was detected or not detected. So it's a binary classification. Because the ionosphere is not detected all around the planet, when it's nighttime, you don't expect to see it because the ionosphere is produced by the solar radiation. Although there are other processes that can produce it as well, like electron precipitation. So we produced or developed a convolutional neural network, which is very good for image classification. The main reason that the convolutional neural network is very good is because it's got this extra section at the start which extracts features from images. So I've done a quick schematic here. So you have this kernel, which is the set of numbers in the square that moves across the image, and each time it moves across the image, it calculates the output of the kernel times the pixel values. And the end result of that is that it can identify the regions in the image which have particular features. So just to give a slightly more concrete example of that, if you have a kernel at the top which is a kind of horizontal kernel, it will move across the image, and every time it finds features where there's a discontinuity in the horizontal direction, it outputs a strong signal in those cases. And the same here with a vertical direction. These are just examples of the kind of outputs, feature maps that you get, so you can see that this one here, it's detected a stronger signal where there's a vertical line in the image. The good thing about the machine learning aspect of this is that you don't actually have to design the kernels yourself. The neural network learns for itself what kind of kernels are the most useful for the features that you're looking for in the images. These are just examples because they're easier to understand and visualize. These are not necessarily the ones that it actually finds the most useful. So we built this classifier. The biggest job was creating the training set, which involved manually classifying thousands of ionograms. That was the big job I had to do, and work out when we got enough. So the bottom graph, you can see where I was trying it with smaller training sets of 3,000 and then 5,000 ionograms, hoping that it would produce good results, but it turned out I had to do a lot. I got up to 20,000, and then that started producing good results. I then expanded it up to 30,000, but I found that beyond that it wasn't really helping, so I stopped there. I thought that's enough, and it seems to be adequate for what we wanted to do. The top graph is trying different architectures of the neural network. So that's adding in extra layers of convolution, extra layers of fully connected nodes. I found that actually adding more didn't always necessarily help. So the blue line shows that when I used a much bigger neural network with millions of parameters, it didn't really have a stable result. It became unstable and it didn't get to as higher accuracy. Whereas the black line is the one we finally used, which achieved a very good accuracy, up to 97.5%. So having done all the development work and tested and validated the classifier, I then applied it to the entire database, which is the 2.3 million ionograms. And you can see the results here. So this is a map of Mars, essentially, but it's looking at the top panel is showing all the places where Mars Express has observed the ionosphere. So for each pixel, there's hundreds of ionograms. That's what's shown in the top panel. So where it's green, you've got hundreds of ionograms. And then the bottom map is the results of the classification. So as I said, it's a binary classification. Blue is where there's very few detections of the ionosphere. Green is where it's detecting the ionosphere, and the results turned out very much as I expected. So the green is on the day side, where the ionosphere is being produced by the solar radiation. The blue areas are the night side, where you wouldn't expect. You do get some patches, which are the red ones, where you do get some electron precipitation causing patchy night side ionosphere. And just for comparison, this is a model based on a simulation, and I was quite happy to see that they turned out very similar. So it looks like not only is the AI working, but also our understanding of the ionosphere is pretty good. Well, it seems to be pretty good. Obviously, more detail is needed. This is similar to the previous map, but in this case, looking at the seasonal variation. So you can see the 4 seasons. I've split the data into 4. The reason you see this kind of white diamond shape is because the way Mars Express orbits, it doesn't always, it never covers that area of the dawn, so it never covers the dawn area. So we just have a gap in the data there, but all the rest of it looks pretty much as you would expect, and you can see that the edges of the ionosphere follow the contours in the solar zenith angle, which is the behaviour you would expect. So that's pretty much the results that we were expecting. I'm now doing a lot more analysis to look at the details of this and compare it to models to see where our understanding of the ionosphere is correct and where it needs improvement. But for now, the classifier is available online. There's a paper about it which was published last year, and there's also on the Leicester archive there's a set of software and the train model which you can use if you want to classify ionograms. So I'll leave it there. Thanks.
Lovely, thank you. We've got an immediate question in the front row just here.
Hi, can you remind us what does Mars have a magnetic field, and how big is the magnetic field?
So Mars has a very unusual, it's not a global magnetic field, but it has crustal regions in the southern hemisphere which have a kind of very localized, complicated magnetic field, but there's no global.
Does that affect what's going on at the 400-kilometer level where the ions are?
Yeah, so in the south, the crustal fields can kind of funnel the precipitating electrons to produce regional
and
patches.
Can you see that in your data?
Well, yeah, I mean, we haven't done an exact mapping of where the crustal field regions are, but that's one thing we're interested in is whether these red patches that you can see align with where the crustal fields are, but that's future work. I haven't done that yet. But that'd be very interesting to look at.
Lovely, thank you. Any more questions?
Thanks for the nice talk. In terms of the training data, do I understand correctly, you classified the 20,000?
Yeah, well, I did most of it, and then I had some students who also helped.
So 2 questions. How much does, so you sort of said at the end, if you want to use this for classifying other ionospheres, how much does that generalize? I mean, is that training data set something that could be used for other applications, other probes, for example?
Yeah, I mean, as long as I think the ionosphere trace in the images is reasonably similar if you're looking at Earth or at Mars. It might need some additional training if you're looking at a different planet, but I think it would probably generalise fairly well. I haven't tried doing that, but I have seen other people trying to do similar things using data at Earth, and I don't see why it wouldn't work. The ionograms look pretty similar. So.
Okay. And then just to follow up, if I can, in terms of like the errors that you make in the training process, is there any way to quantify that? I mean, for example, if you have some systematic error that one of the students was making or something like that, is it possible to dig those out from what you've been doing? Like, I was wondering why the 30,000 was slightly worse, and I wondered, well, I don't know, maybe you got tired and made a few mistakes in there or something. I don't know.
I think I think the main issue is more to do with the composition of the training set. So it's whether it has enough examples of all the, because there's a huge variety of ionograms. I only showed kind of a typical example, but there's a huge variety where they've got lots of different features, magnetic field features, noise, that kind of thing. So it's whether you've got a good mixture of all those things and whether it's well balanced. The way I tried to quantify it was I made a test set of 2,000 ionograms which were selected at random, and classified those manually and then used that as an independent testing set. So that quantifies how well it's doing, but obviously that's still a very small sample. It would be better to use a larger sample. With the biases introduced by different people doing the classification, that could also be an issue because sometimes, I mean, the ones I showed are quite obvious, but there are marginal cases where it's very faint or patchy traces and it's a bit hard to say if it's there or not. So I think at the margins there could be some bias depending on who made the training set, but hopefully those are fairly minimal. It wouldn't affect the main, the majority of the classifications are very certain, so it wouldn't affect most of it, but maybe at the borders where the ionosphere is very faint or patchy, it might affect it in those areas.
Fabulous. I'm so sorry, I'm going to cut questions off there for time, but we'll have the coffee break as well if you want to catch up later.
Hello everyone, my name is Tanya Kushwaha and I'm a final year PhD student at Cardiff University working with Mikako Matsura and Tim Davis on the classification of AGB stars. And today I'll be presenting you some of my results. So one of the major challenges in astronomy is understanding our own galaxy, how Milky Way has formed and evolved over billions of years ago. And one of the tracers to study this is asymptotic giant branch stars, also called AGB stars. These stars are in their late evolutionary phases with masses between 0.8 and 8 solar masses. And they can be used to trace star formation history where stars has been found from 30 million to 10 billion years ago. And there are two chemical types of AGB stars, carbon-rich or oxygen-rich, depending on the mixing processes in these stars. And this carbon-to-oxygen ratio is a very good metallicity tracer in our galaxy. So AGB stars, in a way, act as galactic fossils and can be used to study the evolution and structure of our own galaxy. So when I started my PhD, Gaia DR3 data was published with 1.5 billion data for 1.5 billion stars and low-resolution spectra for 220 million sources. And this was a great opportunity to use machine learning as it provides scalable, efficient, and robust classification. And this was also an opportunity to expand the catalogs of carbon-rich and oxygen-rich AGB stars, because at that time only a few thousand AGB stars were known in our galaxy. And Gaia also provides both photometry and spectroscopy, so this was another opportunity to use multidimensional features, including both photometry and spectroscopy. So in our work, we have used a hybrid learning approach where we have used similarity-based analysis to make a potential AGB candidate catalog from Gaia DR3. And then we have used XGBoost for supervised learning to classify these potential candidates into carbon-rich and oxygen-rich AGB stars. So here I'm showing you an example from our similarity-based analysis where we have used photometric and spectroscopic low-resolution spectra from Gaia to find AGB candidates comparing to the known ones. So on the left-hand side, I'm showing you two spectra. The leftmost one is an oxygen-rich spectra with titanium oxide and vanadium oxide absorption bands. And the red spectra is for a carbon-rich AGB star with carbon features. And on the right-hand side, I'm showing you these potential AGB candidates, which we have found from Gaia for these two. And the first row is the top 5 sources, the top best 5 sources from similarity analysis. So if you see the first 2 columns, the spectra looks very similar to an oxygen-rich AGB star. And the third and the fourth columns are for a carbon-rich spectra. However, if you see the very last column, these are the similar sources for the least 5 similarity scores. And you can see that the spectra differs a little. It's because with lower similarity scores, the features tend to become noisier. And then once we found these AGB candidates, we used XGBoost classifier to classify these candidates further. And we used the same known catalog of AGB candidates to classify these into carbon-rich and oxygen-rich. We divided the catalog into test training set, and there is a difference in the number of stars, as carbon-rich stars are rarer. So we used a weighting between the two, and we used area under the curve for as machine learning metric for our classifier, and we obtained over 300,000 oxygen-rich AGB stars and over 4,000 carbon-rich AGB stars. So here I'm showing you a 2D spatial distribution plot for carbon-rich and oxygen-rich AGB stars, and the blue stars are oxygen-rich AGB stars, and the red distribution is for carbon-rich AGB stars. As you can see, the oxygen-rich AGB stars are concentrated more towards the inner galaxy, whereas carbon-rich stars have a more uniform distribution and are concentrated towards the outer galaxy. We also tried to study galactic warp using AGB stars. Galactic warp is basically a wavy deformation in a spiral arm galaxy. It's basically the deviation from the galactic midplane for larger radial distances. And it has been observed in many galaxies and has also been studied in our galaxy using other stellar sources, such as RR Lyrae and other older sources, Cepheids, as well as H1 gas. And we have found that AGB stars are tracing galactic warp for larger radial distances. So on the left-hand side, I'm showing you a side view plot, so Z versus Y plane. And you can see that there is a larger concentration up to 10 kiloparsec in Y. However, starting from above 10 kiloparsec, there is a deviation from the galactic midplane. And we have also compared this distribution with the results from Cepheids, and we have found that the results are very similar to Cepheids. So AGB stars are potential tracers of galactic warp. And here I'm just showing you two other distributions, so Y versus X plane, where you can see that carbon-rich AGB stars are indeed concentrated towards the outer galactic plane, towards the outer galaxy. And you can also see the effects of interstellar extinction, as we have found fewer sources towards the galactic center. And yeah, this is pretty much my talk. So we use machine learning to classify AGB stars as carbon-rich or oxygen-rich. We have found O-rich AGB stars are distributed more towards the inner galaxy, whereas carbon-rich have a more uniform distribution towards the outer galaxy. And we have found that AGB stars, so these intermediate mass AGB stars, intermediate mass stars can be used as potential tracers of galactic warp. And our future work is to measure the warp amplitude and study mass loss with these stars in our galaxy. Thank you.
Lovely, thank you very much. Have we got any questions? One at the front here.
Why do stars have to choose between O-rich or C-rich? Why can't they have, why do they break down that way?
So AGB stars are mainly of two types, oxygen-rich and carbon-rich. So most of them are oxygen-rich, but there are these third dredge-up mixing processes that happen in these stars, which bring carbon from the core to the outer surfaces in these stars, and this changes the chemical abundances in AGB stars. And this carbon to oxygen ratio in AGB stars is a very good candidate for, is a good tracer for metallicity in our galaxy.
Lovely, thank you. Have we got any other questions? I have a quick one, if not. It looks really exciting, especially the future work. I was just wondering if there's any new or upcoming surveys that you're excited about to help with measuring the warp amplitude.
There is definitely Gaia DR4. It will be, I think, published next year, but I'll be finishing my PhD before that. So we have tried to study warp amplitude with different angles and different Z versus R plots. And I think we are still kind of like, we're not sure of the results, whether it shows a significant like warp amplitude or not with AGB stars, but yeah, we're still working on it.
Okay, fabulous.
Yeah.
Thank you so much, and thank you to all our speakers from the session.
Okay, welcome back, everyone. My name is Shravya Shinoy, and I'll be your chair for the final session of the day. We have 4 talks. First up, Ashley.
Oh, there we go. Let me go back a slide. Okay. Hi, everyone. I'm Ashley Spindler. I'm an academic at the University of Hertfordshire. I first just want to apologise to the organisers, because I personally have been a huge pain in the butt in the organising of this day. I was supposed to be the first talk, and then I double booked myself, and then there's been a bunch of confusion with my slides. So I am very sorry. So I'm going to talk to you about some work I've been doing with segmentation in deep learning with galaxy images. This is work that I'm doing with the Galaxy Zoo research team. It's myself, Mike Walmsley, Tobias Guerin, and Karen Masters. We've been sort of collaborating on segmentation as sort of an interesting field to look at in galaxy images, and particularly galaxy morphology, for the past couple of years. Segmentation is, in my view, kind of the next step from morphology classification, going from just looking at global understandings of what the shapes of galaxies are to being able to map out the specific internal structures, so spiral arms, bars, rings, tidal tails, and sort of merging parts of galaxies. And what's hopefully useful in doing that is being able to look at what the sort of properties of these different structures are in relation to each other, sort of build an understanding of the formation processes and the effects that they're having on their host galaxies. So this work starts actually back in, I think 2019 is when Galaxy Zoo 3D kicked off, which was a citizen science program to identify internal structures of galaxies using the Galaxy Zoo platform. This was performed on galaxies in the parent sample of Manga, which is 30 to 40,000 galaxies, of which 10,000 were observed with the IFU in the Manga survey. And what I've done is I've taken the sort of 7,500 galaxies in that sample that have spiral arms and used that as a training set on a deep segmentation model to produce segmentation maps for spiral arms and bars. The type of model we've used is called a UNet. The numbers on here are not exactly what the model is. But if you haven't seen a UNet before, but you've seen autoencoders, these are sort of similar-ish models. The main difference is there are these skip connections between stages in the encoder part of the model to the decoder, which essentially allows you to project spatial information from the encoder into the decoder, which UNets sort of started in the medical field specifically for segmentation. And then the main difference between classic UNets and what we've done is instead of doing sort of a classification on a binary label, on a binary segmentation map, we've asked the model to essentially do a regression task and predict the vote fraction from the number of volunteers who enclosed a pixel in their diagrams. So the results from this have been incredibly promising. This is sort of a wide range of galaxies of different properties. What we've done is predict spiral arm and bar masks on a what I call a dirty sample of around 650,000 galaxies from the DESI survey. So some of these may be questionably spirals, but most of them are spirals. And some of them have bars, which is what the sort of delineation in these plots are. So in the top left corner there, you see very strongly barred galaxies, and then in the bottom right is sort of spirals without bars. And now the really important thing, I think, in any machine learning application in astronomy is where's the physics? And so we're able to do some cool physics with this. That plot hasn't worked. That's fine. So we're able to measure bar lengths using the segmentation maps. What this plot should show is there are predicted bar lengths from the segmentation maps line up with the bar lengths that were found in Hoyle 2011, which was a Galaxy Zoo citizen science project to measure bar lengths, which makes sense when you think about it. We're using a model trained on the same idea of looking at how big the bar is. We're able to line these maps up with IFU data cubes, which is generally quite easy. So this is an example of an H-alpha map from Manga in a spiral galaxy, and you can see in the both the radial and the azimuthal distribution here how how the H-alpha is distributed through the disk of these galaxies. That's generally quite easy. It's slightly more difficult with photometry, just because you kind of got to decide the threshold levels, which is a little bit more difficult in with the photometric data, just when you're dealing with very large numbers of galaxies. We've kind of settled on doing a weird percentile cut, which I'm happy to talk about at some point if anyone wants to hear about that. But we are able to, again, sort of reproduce normal physics results. So the plot on the left here is showing the median colors of pixels in the bar and not in the bar for barred galaxies, and hopefully you will all agree with me here that the sort of barred pixels are shifted to the red end here, which is what we expect. Bars are typically redder than the disks that they live in. And then anyone who might have seen my talk at NAM might remember that I could not get the spiral arms to work. I had a really big problem where my spiral arms were actually bluer than the rest of were redder than the rest of the disk, which is not correct, but I fixed it. And this next plot is showing radially what the median color of the spiral arms and the interarm regions, and seeing that the spiral arms are bluer or are less red, because we don't have a blue color in here, but are less red. So there's fewer old stars, so there's more star formation happening in those sort of high density regions of the bars. And then the last really cool, interesting thing that comes out of this is a piece of what I say is emergent behavior. This model was not trained on any rings. There are 0 rings in the training data. But when we present the model with ringed galaxies, and this is a subset of galaxies that was put together by Mike Walmsley and James Dawson, we can see that the model actually predicts rings incredibly well. And I'm hoping now to use this to dig into ring behavior. Okay, yeah, I can stop there.
Any questions for Ashley online or in person? One online?
Yeah, we have one online. Fabulous. So this is a question from Rajit Shrivastava. And it just says, I was wondering about the computational performance of the model.
what is the typical inference time per galaxy? And for the Hoyle dataset, how were the segmentation outputs calibrated, and how was the bar length derived and matched to the catalog definitions?
Okay, so how long does it take? I can say that for the full data set, so for 650-ish thousand galaxies, it takes about 30 minutes to produce all of the segmentation maps, which is very, very fast when you do the maps per galaxy. How the maps calibrated? That's a really good question. I mean, kind of not very well. So one of the quirks of the UNet is that the maximum pixel intensity that comes out in the segmentation map is tied quite directly to the maximum brightness in the galaxy image. And one of the things that we've had difficulty with in working out the threshold cuts in the segmentation maps is dealing with that problem, because if you have a dimmer galaxy, even if it's got an obvious spiral arm, that might not show up as brightly in the segmentation maps. And so we've done some things, mainly using percentile cuts, to try and get a uniform way of thresholding the maps. The bar lengths were, I can't remember where that plot is now, it doesn't matter. Just a really naively done, just looking for, I think, the 95% inclusion in the horizontal and vertical, and then calculating the length from that.
Okay, in the interest of time, let's move on to the next talk. Let's thank Ashley. Next up, we have Alex. Thank you.
Okay. I haven't checked my slides, so let's hope they work. Yeah, okay. Good afternoon, everyone. I'm Alex. I am a postdoc based in Oxford. I'm interested in transients, particularly finding transients with radio telescopes. I'm going to be telling you how I've been doing that with an eye towards the SKA. So the problem is kind of a problem that machine learning is often invoked. We have lots of data and not enough time to look at it all. In particular, when the SKA comes online in a few years' time, it will take so much data that we won't be able to store it in perpetuity. I'm interested in transients, so I want to find these transients before they fade from the sky, but we also need to find them before we delete them forever from our servers. Like, quite genuinely, that is the case. So when we have really high-quality images like this is taken from the Meerkat telescope, of lots of potentially interesting things, I want to find transients. They consist of maybe 1% at most of our data. I want to find them quickly before we can never find them again. So I'm going to show you how I've done that with a precursor survey on the ASCAP telescope in Australia. So this is the VAST survey. This is kind of a transient finding survey on ASCAP. This is its footprint. I'm going to tell you about the galactic plane part. You can see galactic plane nicely highlighted in sort of yellow here. It's been targeted sort of every fortnight for about a few years, and two spots for the L and SMCs as well. This is a relatively shallow survey, but taking very consistent data over several years, builds me a sort of big bucket of 45,000 light curves, and I say, what's the weirdest thing in that big bucket of 45,000 light curves, and how quickly can we find them, and what are they, etc. To do this, I've used the astronomy package developed by Michelle Lochner and Bruce Bassett. It's a really great tool if you're interested in playing with anomaly detection techniques. Then please come chat with me. It's very simple. We extract some features from my light curves that are just, my light curves are just plots of brightness over time. That's all I'm dealing with here. We do some kind of anomaly detection, and the real key step is this active learning loop, where example transients are shown to me, and then I label a sort of small subsample of them in a kind of Netflix style, show me more rom-coms, show me less crime thrillers or whatever, and then you sort of repeat that loop ad nauseum until you have hopefully a well-calibrated list of sources from most to least anomalous, and then you can go through that list and say, what are the things that I find, what's interesting doing astrophysics on that list. So the features I use are parametric ones. I'm not doing any fun deep learning. We're going to keep it nice and simple. Things like amplitudes or widths or slopes on a light curve, a few low-order Fourier terms, means, standard deviations, and skews. These are all fairly simple terms in this feats package, but they calculate very quickly, which is nice. Some of these features are known to correlate with astrophysical phenomena. Some of them are just, parametric features that we can calculate easily. And of course, feature choice is absolutely crucial to finding the thing you care about. Things like there's going to be no interesting morphological information here because these are univariate light curves with variability parameters to measure them. That's always, you've got to use the right features for the right job. But I want to point you to some work that I've done with Xijing Fu here for investigating using Gaussian processes for feature extraction. So just highlighting that. The anomaly detection that is built into astronomy, there are some very simple baked-in models, built-in models, local outlier factors and isolation forests, both fairly simple. They both perform pretty similarly. I'm going to use the LOF. If you want to know why, you can ask me later. It's not super important, but they both perform about the same. It's worth asking, what do we mean when I say something's anomalous? My actual science case is like nearby flaring stars and what that means for habitability. And I'm also interested in black holes and interesting X-ray binaries and that kind of thing. But to someone who designs pipelines, perhaps finding imaging artifacts is the thing that's anomalous to them. So it's worth thinking where in this space of is something weird, is something interesting, is something unusual, where does the thing you care about lie, and are you doing the kind of thing to find it correctly? And credit to Chris Lintott who inspired that. The active learning presents me a nice kind of graphical interface, shows me a light curve, and I say, yeah, I rate that 5 out of 5, show me more of those, or I can rank it as 0 out of 5, show me less of those, and I say you repeat that until you can no longer be bothered, basically. I probably labelled a couple of hundred things out of my 45,000 in total. It takes a few days' work, it's not that difficult. And I have now a list of sources from most to least anomalous. What shows up in the sort of cream of the crop? What is the most anomalous thing in that list? That's kind of the million-dollar question. Where's the proof in the pudding? So we've seen some of these sort of U-maps before. These are kind of two-dimensional representations of our space. And this is coloured by this anomaly score. So yellow means kind of more anomalous. And you can see there are only just a few small areas of this figure that are sort of highlighted as having highly anomalous things. And this makes sense. Our anomalies are rare. They should exist in only small parts of the data. And when we investigate those parts of the data, we see a whole range of interesting science. So I just highlight a few examples here. There's an interesting X-ray binary that we've been following. Thank you. This is a colliding stellar wind binary, and this is a long-period transient. I'm going to highlight that one in particular. This source, JPM J1839-10, was discovered 3 years ago and kind of spawned its own field within radio transients. This is like the prototypical example of this class of objects that didn't exist until 3 years ago. This thing shows up as the most anomalous thing in my pile of data. So it's quite nice that the algorithm finds it to be very anomalous, and astronomers have found it to be very anomalous. It sort of spawned a whole new field of things. So that's kind of good that those things match. Also found a really interesting X-ray binary. This is perhaps a not particularly exciting light curve, but you can see very occasional flares from this thing. These are when a neutral star reaches periastron in a high-mass X-ray binary system. We've seen a few of this kind of system in the Milky Way, and they're typically very faint. This one is very detectable and is in the LMC, so it must be orders of magnitude more luminous. So it's a very extreme example of this class. And this is being led by a PhD student, Justine, in Oxford. So we're finding a whole range of interesting anomalous things. We also find things that the survey had already found, so we have some belief in our maybe not completeness, but that we're not missing too many things. They'd already reported on these nova outbursts, and we find those in the top couple of hundred most anomalous things in our list as well. So that's good as well. Also find sort of less extreme, kind of moderate variability things, kind of weird pulsars doing strange things. Not super important the details, but nulling and intermittent behaviour from interesting pulsars. Final thing I wanted to show is we're thinking about, I said we calculate all these features, which ones are doing the heavy lifting? And to do that, what I've done is calculate the mutual information between my distribution of anomaly scores and the distribution of all of my features. I'm not going to go through what each of them means, but this mutual information is a kind of like a non-linear form of a correlation test, if you like. And I'm interested in transient and variable things, so it's no surprise, perhaps, that things like the amplitude or the standard deviation, the spread of points in my light curve show up as having the most mutual information as our anomaly score. So it's worth checking to see which of your features are doing the thing that you hope they are to find the thing you care about, if that makes sense. Okay, that's everything. These techniques are really fun, they're really fast, and really flexible. We found a bunch of interesting things, and if you have piles of data you want to find interesting things in, then let's chat. Thank you very much.
thanks for an interesting talk. You mentioned very briefly deep learning.
Yes.
I'm curious, really, if you have any sense to what extent it would improve it using the full light curve compared with the feature extracted version.
Yeah, it's a good question. Yeah, I haven't tried it in truth. I suspect that it probably would be useful to see, and learning from that latent space, what do each of the the variables in that actually correspond to. I think that's worth doing. I think the first stage kind of, and maybe this is the kind of pragmatist view, is like, what's the interesting things we found and publishing those first, and then exploring the technique later. I don't know. So, but I think I don't know. I think it probably would be better.
It has been done on spectra, for example.
Yes. Yeah.
By some people here. So I think
give it a go. Yeah.
Is there,
Yeah. No, I agree.
One quick question.
In terms of that anomalous radio transit you were showing us, it's spawned this whole. That seems super cool. Does the community have a vague idea about what that is, or is it still too early to tell? It's a complete unknown at this point.
Yeah. So these long period transits. Yeah. So they've only been around for a couple of years. We've seen, and most of them are found actually by a slightly different technique. But the few that have been found, the few that have multi-wavelength counterparts, seem to be probably some kind of interesting white dwarf binary behavior, a white dwarf and M dwarf probably, and some strange magnetic behavior going on, but it's not completely settled. But it's this field is 2.5 years old, so that's probably what they are, but it's not settled. Yeah.
Okay, great. Let's thank Alex again.
I think that's where it's supposed to be. No. Sorry, it says end of slideshow. Back. Oh, thanks.
Hi everyone, my name is Federica Rescigno. I'm a postdoc at the University of Birmingham, and today we'll be talking about how I'm currently recalibrating the Bison datasets with neural networks and physics-aware loss design. So let's get started. I am first and foremost an exoplanetologist. So what I want to do in my job is detect exoplanets, and in particular, I focus on rocky Earth-like exoplanets with the eventual possibility of life. Now, this is what I want to do. However, I cannot do it easily because stars are not static objects. I use a technique called the radial velocity method, which means I look at the Doppler shift of stellar spectral lines. But spectral lines can be deformed and shifted by a variety of other things happening on the surface of the star. I'm talking star spots and faculae, any kind of magnetic activity, oscillations, flares. All of these effects create spurious signal in the radial velocities that can completely hide or mimic the presence of a planet. And in particular here, I have a real data set. This is the stellar activity of a normal quiet star. And in blue, I've plotted the signal that we would need to find if we were to detect the Earth around a sun-like star. So before we even hope to find Earth-like planets, we need to wade through several meters per second worth of stellar activity. And this is a quiet star. So how do we do it? Well, it's particularly hard because all of these effects are very degenerate in spatial distribution. So what we can do at the moment is to use the one star we can resolve. So we're starting from the sun. We have a wealth of data, a wealth of solar data, both resolved and disk integrated. So what we can do is we can start studying the stellar activity signals in the sun to then model and understand their behaviors and then extrapolate to other sun-like stars. This is where telescopes like the Birmingham Solar Oscillation Network, or BISON, come into play. BISON is a fleet of 7 if you count the one in Birmingham, but it doesn't really see the sun, telescopes scattered around the globe. They've been observing the sun since 1975 with a 40-second cadence. And altogether, there's a structure and they're positioned in a way so that they can observe the sun continuously. We have about 40 million data points. So quite a lot of data. We can do a lot with it. However, we have a problem. The BISON telescopes were made in 1975, and they haven't really changed since. So the BISON data is really dominated by instrumental effects and other solar system systematics. So as an example here, this is on the y-axis the BISON data, what we have, And I've plotted it against day and the year, and you can see this nice sinusoidal, who's not real. This is not solar signals. This is just the Earth orbiting around the sun. And if I zoom in, I can see this nice S shape that is just the Earth spinning on its axis. And here, I also plotted them against air mass, and you can clearly see how when the sun dips below starts dipping below the horizon, we can see a large distortion in the signal. So all of these effects completely, totally obscure the signals we're hoping to study, the solar activity signals. So what do? We have 40 million data points. So let's see what we can do with neural networks. So what we thought about doing originally is that we want to essentially calibrate out all instrumental and solar system effects using neural networks. And then we want to keep the solar signals, solar activity, as leftover. We explicitly want to keep it as leftover because we don't want to just predict it. We need to study in a variety of ways. So we want essentially the neural network not to eat it up. So we work on the assumption that as long as we feed the neural network only features that explicitly do not describe solar signals, this should be fine, and we should be able to calibrate the noise signals without destroying the solar activity signal. However, we have another issue. Each station is slightly different, and it's in a different position on Earth, and you observe the sun at different times, so they all have to be dealt with individually, because they all have different features that they need to be given. So let's start with the simplest model that we did for phase 1. This is just a simple neural network. We just used a 6-layer, 32-neuron structure with EDO activation functions and simple student T loss function. And we feed it a series of features. It goes from the time in the day, the air mass, the day in the year, and we expect it to predict our bison, our data, our bison RVs. This does quite well. Here you can see prediction on the y-axis and the real data on the x-axis. And it does fine, but unfortunately it doesn't do as well as we're hoping. And although it does reduce the noise down to less than 1% of the original signals, it's still large enough to obscure solar activity. And if we increase flexibility, we just start eating up solar activity. So what do? We rely on the fact that the Birmingham solar oscillation is a fleet. So some of them will be observing the sun at the same time. So we use that in our neural network. We have essentially a phase 2. We organize so that we have one mini neural network predicting the bison RVs, the bison data for each station individually. They're all be given different features. And then we have a second layer. Here we subtract our prediction from the data, which ideally should only leave solar activity left over. And then what we do a scatter loss computations to find the true simultaneous solar RV. And in this way, this is preliminary, we're doing really, really well. And we're not eating up solar activity. And that's the important part. So what we did overall is we know we want to use neural networks. We have so much data, and these noise signals are very, very complex. There's no simple models for them. So using neural network is perfect for things like this. However, we need to be careful because the neural networks are as good as predicted things as they're good at eating signals. So we want to make sure that we include science in it, which is why we have this physics-aware loss design. And at the end of this research, our expected output is the highest fidelity long baseline RV dataset available for any stars, which we will use to study stellar and solar activity over decades. Thank you very much.
Perfectly on time. Any questions?
So you did day and seasons, etc. Did you look? You said it was over 40 years. Was there periodicity being entered in from the sun being cyclical over those 40 years as well, or were you able to just take that out because that's really well known?
No, we want that. So we're actually working really, really hard to make sure we keep that, because magnetic activity, magnetic cycles are really, really important to understand from a stellar activity point of view. So we actually had to jump through quite a few hoops to make sure that the features we use don't eat that up.
Any other questions?
I was wondering if you would be able to also add in data like UV data or X-ray data, which might help because they're more sensitive to stellar activity. So would that help?
So at the moment, what we're doing is calibrating for everything that's not stellar activity. So one way we could be using that is to kind of essentially use it as at the stage of do not remove this signal. However, there's no direct correlation to like the signal we would get, for example, in X-ray from faculae and the one we would get in optical RV. So it is a bit more complicated. What we're aiming to do is after we do this first pass, when we have the solar activity, we want to have essentially a phase 3, which we actually try to model it, giving it features to explain solar activity all at the same time. However, the field also wants to use this data set to do Gaussian process with non-stationary kernel analysis and things like that. So at the moment, that's considered phase 3.
Okay, thanks.
Let's thank Federica.
Thank you very much.
We have a final talk by Reese.
Cool. End of the day, I get to bore you to sleep. Hi, I'm Reese. For those of you I'm from Sussex, background in X-ray and optical astronomy, but this is not really to do with specifically an application of machine learning or an application of astronomy, but a tool that should hopefully address a problem that I hope, actually, quick show of hands, who here has labelled or classified or visually inspected errors or input data for their machine learning models? How much did you love it? So, the motivations for this is, if you're not familiar with GIGO, garbage in, garbage out. I was told not to move, sorry. I'm a wobbly person. You're expecting that if you're not generating your own data set, someone's going to hand you, I have infrastructure background as well, someone's going to hand you some lovely, perfect cabling into your computing systems. In actual fact, this is the spaghetti that you're more likely to get in your data. You're not going to get perfect truths. You're not going to get the best sample that you're ever going to get. And so you're always going to have to do some data cleaning. And you're also going to really have a hard look at what does truth mean in order for your machine learning algorithm to also find out what the truth is. We're also entering, so the astronomy bit comes in now, large-scale surveys. We have footprints that basically cover the sky. I was chatting to someone at the coffee break earlier who was talking about terabytes and terabytes, and you've got some stations where they're throwing away 99% of their data because they can't analyze it fast enough. So if you're going to be doing that, we're going to need machine learning automated finders, or at least some kind of automation. But even if you're not using machine learning, you still need a truthful set to test any algorithmic approaches. And so if you've got garbage coming in, that's going to, even if it's only 1% of your data is garbage, that's going to constrain your output and your accuracy unless you find some way to constrain how much of your data is nonsense. So this is targeted things like contamination, segmentation, signal-to-noise problems, and then fantastically rare objects. And the key bit here is this software that I mentioned. It's called Octavius. It's a constrained acronym because astronomy. And so it's aiming at making this limited expert time. So your best experts, the people who can look at an image and classify it in a second, have the least amount of time through their jobs, through other applications to actually give it to you. Whereas you might have, if you're lucky, say 20 undergraduates or PhD students that you can just bribe them with cookies and cakes and things to get them to sit there for hours and hours and hours and then pay for their glasses. So the design of Octavius, so it's the main thing of this is that it's a web-based tool, and so it's been containerized so that it will be able to deploy on pretty much any Linux-based system. If you have Windows, go away. It does work on it. I'm not helping you. We've got this secure API middleware. The reason for this is if you work with LSST or Euclid or Big Sky surveys, that data is embargoed. So we need a secure way to access the data or have it placed behind, and you then securely access this application. The front end is a React Native, so JavaScript, it's a browser. And so we have this split into things like users and also organizations, so you don't have to deploy this 20 times. If you're working on Rubin and then LSST and then something else, we can securely handle, you're in Rubin but not LSST, you're in Brighton but you're not in Birmingham, so you can see these things and that's all handled for you. And then in the back end, because everyone likes the back end and handling it as well as is that we've got this MongoDB database. And the reason we're not relational is that we don't know what your data looks like. And you don't know what your data might look like in 6 years' time towards the end of your survey. And so we can't use a relational database because otherwise we have to restructure it every 20 minutes. Sorry, every 20 years, sorry. And then the last bit is obviously the analytics and querying, the ability to have a look at this metrics. And the key thing that someone brought up earlier, one thing that we do is we track, I come from, I used to do ad-based stuff for companies. I track everything, we track everything the user does. It is atomic. Every single interaction with the service is monitored. And the reason for that is if you're used to machine learning, MCMC, you've got a burn-in time. Humans have a burn-in time when they're classifying. The first 10 minutes of their session, they are not as good as when they're in that flow state of actually clicking through and classifying things. And they're not if they're sat there for 10 hours because they're like, I've just got 5,000 to go. At the end, they're also worse. And so we need to constrain that so that when you're looking at your truth set, you understand, you can put errors on how truthy your actual object is, so that you can put that all the way through whatever machine learning you want to do. Here's an example use case that we're attempting to do with LSST, which is you've got your telescope and your normal data reduction pipelines, etc. You have your AI model. I've picked DCNN because that's my favorite. It's, it might be finding galaxy clusters here, so that's the one I've picked. But you can put any model here. It's feeding into Octavius through the API and the secure integration. So it's not a separate pipeline from your normal data reductions. The idea is it can sit next to it and be fed into as you're generating all of your metadata from your telescopes as well as your optical images. We're not losing that. And so, you feed that into your AI. The AI is going to give a prediction, and then the key bit here is you've got online reinforcement. So when the AI, because we've got the original training set that you did before the telescope went live in your commissioning phase, where you had some error on your inputs, your AI model can say, I have no idea, or I'm not confident on this result. I think it's a cluster. I think this is an AGN, but I'm not sure. This can be fed back into Octavius where someone logs in and they can be the expert, the top-end person, and they can securely flag it or classify it. And then, we can feed that back to what I'm going to call the engineers. So this is the idea that you have an astronomer over here and someone who knows computing over here. And so you can feed back and they can then retrain, either automatically, because it's an API, it can feed things back to your HPC cluster if you're using a private cloud, or it can just be a task for some engineer to do every 2 months, for example. Or you can just freeze it. So many surveys, you want to freeze what applications and have version release. That's it, basically. So the best way to answer questions, I think, is just to have a demo in the background. So if the question is asked and it's mind-numbingly boring, you can just look at that instead. So this is an application use where it's just allowing you to move around. It's got integrations with things like Aladdin. So if we cover lots of surveys automatically, we allow for things like nearest neighbours finding. So unlike Galaxy Zoo, where you only see one, we give you a table of them so you can find self-similar objects where, say, a galaxy cluster has been split into 3 objects. That's terrible for your machine learning algorithm to try and learn when you just wanted it to pick out one. But yeah.
Any questions for me?
It's a very nice talk, thank you. The expert review step seems to be the rate-limiting step in the process. How do you keep the number of sort of items that the expert has to review down to a sort of sensible level?
So this was just an example use case of an online reinforcement platform. It's the idea that you already have something trained, and this shows the bit that a lot of classifying tools don't have with online reinforcement. The main bit here is, yes, you still need a large amount of training. The key bit here is that your machine learning algorithm, if you used Octavius to generate your original truth set, and we've been using it for a few years now at Sussex, and it has confidence on that classification. So my boss there, Kathy Roma, is an expert in X-ray, and when she gives a classification, she's 99% of the time right. Paul is slightly better, and that's her postdoc, and postdocs can argue this later. But then we have a whole host of students, and we have more classifications done, and we have that range, that confidence interval, and the session time, so that any classification that we go into an algorithm, you do get a confidence out, so you can pick that cutoff. So if you only want to be 99% sure, you can throw away a lot of stuff, and you can say, I only want 50 objects, and so you just look at 50, or I only want 25. You can limit it that way if you just want to be nicer, but you have the ability with this to go as big as you want, or as small. And the key thing here is it's tiny, this application. It runs on 1 core and 4 gig per 10 users using it. That's the whole point, is that it runs. Sorry.
In the interest of time, let's
yeah,
thank
my
you.
graph.
Okay, so that brings us to the end of this specialist discussion meeting. I want to take 1 minute to thank all of you for being here in person as well as online. I want to thank Colin upstairs, who helped us with all the logistics. I want to thank people at the RAS and Geological Society, Jessica, Richard, and Jenny for helping us with all the logistics side of things. And on behalf of the Scientific Organizing Committee, I'd like to thank Professor Stephen Sargent and Seb Oliver. This was their brainchild, basically, so I'm glad they let us organize and helped us and guided us throughout the way. So thank you. Thank you all for coming, and have a lovely rest of your evening.
And thank you to the SOC as well.